свържем към лаптоп. Той е жемай. Добре. На телевизорите се вижда, нали? Свършите, няма проблем, да се попърна.
Тях че сега Боби е си вика, какво става там. Няма, това просто ще...
Коя страна? На него, от другата?
От другата, да. Чакай да видим. Дали да не го пъкнем отдолу?
Аз съм го пъкнал отдолу. Мисля, виж откъде минава, тук отдолу.
Ами да, може би тогава просто да го изтеглим оттам и да си го вкараме.
Така готово.
Защото тук ще ми се пречка и е точно зад това ме притеснява.
Добре.
Хайде отдолу да е, да. Че микрофона ми е много... Добре.
Дайте, остете. Направо ще го... Не помня, тук ще го прибера под моето.
Добре, видяхме, че работим. Няма да сложим на пауза.
Мисля, че се чуват идеално. Само дете до краят на залата и ми кажете дали там се чува.
Good morning, Lily. How are you? Good to see you. Okay, good morning. How are you? Fine, you? I'm doing well, thank you.
Микрофон добре ще, нали?
Много добре се чувам.
Well, it's not. It's not. Still very
Sofia, good morning. Oh, congratulations.
Thank you very much. And thank you for coming.
But I have to leave tonight. I'm so sorry for this. Obligations.
But I've never to do this next time.
Okay, let's Sofia.
You don't. You're missing. They see what's in your eyes, but they don't see the rest of your facial features. That will obscure thought. So you're resting well. It's not funny.
Nice to meet you. The scenario is the following. First, we will spend, let's say, 15 minutes for the opera. And then Julian will take the floor and he will start the support himself. Okay. When you are ready? Tomorrow. Oh. Why?
Yes, yes,
Yes, yes. Okay. Oh, yeah. Todor, this Professor Koncevic.
Yeah. No, actually, a little bit, yeah. I can see the research.
Да.
Ами да, но това не пречи да е командировано в
Вие радно се те са по-специализирани. Нали? Това е къде? Аз съм идвал прямо за лекции по здраве. Да. Вярно. Да, ние кой го ще там са романка там са много меки хора, много са приятели. И голяма школа ще бъде голяма. Да. Ешо, ела си. Да, извинявайте, ние поне добре, така че почваме да. Аз с Клип. Аз па не знам как трябва да ги предупредим.
Това ще го стримате или да не предам?
Стримаме ли го това?
Той ще го пак го предам на Юлиан и Юлиан ще го веде. А ти те? Аз ще кажа нещо тогава да те на програмите написано ли?
Ами ясно, смяташ, че много време ще имате. Така ли? Аз мисля да 5 минути не повече.
Добре. Okay. Good morning, everybody. Mr. President of the Bulgarian Academy of Sciences, Professor Revalski, distinguished guests, dear colleagues and friends. I'm really excited to see so many brilliant mathematicians here and many friends from all over the world. And I would like warmly to welcome you to the inaugural conference of the International Center for Mathematical Sciences in Sofia. Our center was created after many inspiring discussions of Professor Revalski with various members of the mathematical community in Bulgaria and the Bulgarian mathematical diaspora. During the Mathematics Days in Sofia conferences initiated by him. I would like to emphasize the great role of Professor Sendov, the first director of our center, Professor Lyudmil Katsarkov, who is scientific director of the ICMS, and many other colleagues from the Institute of Mathematics and Informatics of the Bulgarian Academy of Sciences. Among them, I would like to mention the former director of our institute, Professor Drensky, the president of the Bulgarian Academy of the Union of the Bulgarian Mathematicians, Professor Nikolai Nikolov, Professor Vili Milusheva, and our young colleague, Dr. Rangachev. At the beginning of 2020, the center was already present on the European and the world mathematical scene. And this became possible thanks to the financial support of the Bulgarian Academy of Sciences and the Ministry of Education and Science. Unfortunately, the pandemic came that year, and all the events we organized until June 2022 were online. Using sports terminology, I would say that this period of our work was a warming up for the long, I hope, mathematical run of the center. This is the place to thank very much Professor Steve Cantrell, the director of the Institute of Mathematical Sciences of the Americas in Miami, which is a partner of ICMS, Professor Mina Teicher, the director of the Amin Yoter Institute for Mathematics in Israel, and Professor Philip Griffiths, who needs no introduction, for their constant and very valuable practical and scientific support. Thank you very much. A month ago, the center received a great recognition for its work over the past 3 years. Professor Yuri Chinkel, Director of Mathematics and Physical Sciences Division of Simons Foundation, during his visit to Sofia, announced that the International Center for Mathematical Sciences received a generous 3-year grant from the foundation. This, together with the financial support of the Ministry of Education and Sciences, gives a solid financial basis for the work of the center in the next 3-4 years. Ladies and gentlemen, it's time to give the floor to Professor Lyudmil Katsarkov, Scientific Director of the International Center for Mathematical Sciences. Please, Lyudmil.
Thank you all. First of all, let me thank all of you for finding time in your busy schedules to make it to Sofia. So, when I was a graduate student, I was doing different things in math, which actually Philip made me return. did this with a pleasure, but I was around Friedrich Hitzebruch for some time. And so paraphrasing Beatles, what he told me is, love is not what you need a little bit of funds. But in fact, love is the most important thing. And indeed, with a lot of love and inspiration, so this center was created by Bulgarian mathematicians. I mean, I would like again to emphasize the participation of academic Revalski, of academician Sendov, academician Mushkarov, Verichka Milusheva, and many, many other Bulgarian mathematicians. So we wanted to have this type of center that give us the opportunity to communicate with each other, give us the opportunity to get to the cutting-edge research. And let me briefly tell you about this center here. So the mission is fivefold. As I mentioned, is to facilitate research in math and its application, to disseminate the advanced results, to build national and international capacity, to help facilitate the involvement of Bulgarian mathematicians in European and international projects. So one of them is a project that Professor Steve Cantrell is going to tell us about. And to help reintegration of the process of reintegration of young and not so young Bulgarian mathematicians back to the venue of Bulgarian mathematics. So once again, I mean, so it was created with the opinions and the inspiration of many Bulgarian mathematicians. So some of them were mentioned, but it's really the whole Bulgarian community. I mean, so I would like to mention Veselin Petkov and Lachezar Avramov, who actually had contributed to the discussion to this of the creation of this center. I mean, in fact, I was only helping a little bit with the organization. It was really what these people really did. And so we are very happy to finally have this inaugurational conference, which was scheduled to happen 2 years ago. So we are also very grateful to the support by Ministry of Science and Education, initially by Minister Volchev and Deputy Minister Angelieva. And then, of course, we have received quite a bit of support by academician Denkov and the new staff of the ministry. So, of course, as Oleg mentioned, an important contribution was made by Simons Foundation, and so we are very happy for this support, and we'll do our best to continue the collaboration with the Simons Foundation in the future. So in a little bit difficult times, we already have organized some events. So one of them is the series of distinguished lecture series organized with other institutions of the world. So we have also started the initiative of women conferences in Southeastern Europe. So celebration of Bogoslav Sendov's mathematical achievements by talk of Terence Tao, which was very well received, and also traditional annual conference of young Bulgarian mathematicians. We just had one last month, and we intend to continue this in the future as a very important tool in our reintegration process. So I would like to mention a couple of other activities. So this is the conference of metric geometry of the singularities. It was online. Then the visit of Nina Tasher and Stephen Cantrell last year. So the annual conference of women in mathematics. This conference on young Bulgarian mathematicians with a special guest this year, Professor Yuri Chinkel, and we finally come to the event which we are all at, finally, the inaugural conference of this international center, which starts now. So the future plans for this year, of course, is a conference in geometry and physics, which starts immediately after this inaugural conference, conflicts in complex analysis in applications happening in October, and of course the traditional conference on women in mathematics in Southeastern Europe. So there are other events which are being organized at the moment in collaboration with other institutions in Europe. And that's what we plan to do. So we have already established collaboration with the center, the institute in Miami, IMSA, and Steve is going to tell you about this. And so we're in the process of organizing other collaborations of this type with leading institutions in Europe and in the world. So once again, thank you very much for coming. So I promise you a very good conference. You won't regret it. And so let me give the word back to Oleg Pushkarov.
Thank you. Thank you, Lyudmila. Now, I give the floor to Professor Petrova, the Deputy Minister of Education and Science. Please, Professor.
Good morning, everybody. We are academician Julian Revalski, distinguished guests, Professor Bourguignon, Professor Griffith, Professor Cantrell, Professor Lupercio, Professor Barton, Professor Koncevic, and Professor Vyazovska. I'm really honored to welcome you, first in Bulgaria and second on the current conference, on behalf of the Ministry of Education and Science, and mainly on behalf of Academician Nikolai Denko, that is our minister nowadays. Talking from mathematics and from the mathematicians is not an easy task, because as far we all know, mathematics is considered as a queen of sciences, and it is really true. We cannot do just one step without mathematics, because we have to count it and to see what will be the next step. So this is for sure the most important conference for mathematicians nowadays, and I'm very happy that this initiative of the International Center for Mathematical Sciences finally was able to be organized and to gather together so many distinguished guests and brilliant mathematicians. I'm really sure that you will have a very pleasant and very fruitful conference. And also, I would like to connect the current policy of the Ministry of Education with two major goals of the International Center for Mathematical Sciences. The first one is working with young people. As far as you know, the Ministry of Education did a lot of activities. We recently published a grant for the postdoctoral students, for young scientists also, and we continuously support internationally and theoretically the building of the mathematical society in the country. The second most important activity is that this center is collecting the Bulgarian diaspora, which is in the other countries, and that's why this conference will be very useful for mutual exchange of the knowledge, of the views, of the tendencies of the contemporary sciences. And the third thing that is very important for myself is that this conference and this center are trying to position the Central and Eastern Europe in the center of the mathematical world. And I'm sure that this will be done, because Bulgaria is having traditionally very, very high achievements in the mathematical area. Our children at school every year brings us a lot of awards from the international conferences. And this is possible because of you, actually, because of the Bulgarian teachers, because of the Bulgarian university professors and scientists. Just go ahead and do not only one, but many, many steps in this direction. Wish you success.
Thank you very much. Dear friends, I'm sure we will have one more friend in the ministry, because as far as I understood this morning, Professor Petrova graduated the mathematical school, the famous mathematical school in Yambol. Yeah. So, okay. So now I would like to welcome Professor Steve Cantrell to greet the participants in the conference. So I consider, and I think that Professor Cantrell is a big friend of our center, so please.
It's what I get for trying to be inconspicuous. It's really a pleasure to be here again. This is my second visit to Bulgaria, and I send warm greetings from everywhere at the University of Miami, particularly for our Institute of Mathematical Sciences, the Americas. The ICMS has become a really remarkable partner with us, and we have sponsored so far 6 joint postdoctoral scholars, and I hope this becomes a model for things that we can expand to have an international network of exchange going forward in the future. It's also been the case that never waste a good disaster. During the pandemic, we started a really very remarkable series of distinguished colloquium lectures by some of the very finest mathematicians in the world, and that's been another output of this thing, and so it's just been really great. Thank you very much.
Thank you very much. And now I give the floor to the director of the Institute of Mathematics and Informatics at the Bulgarian Academy of Sciences, Professor Peter Boyvarekov. Please, Peter.
Thank you. I will show the time is running. So dear Deputy Minister of Education and Science, the President of the Academy, we're happy with this conference. Despite the COVID-related delay, the Institute and the Center stand strong with this conference, with the participation. Thank you all speakers. Thank you that you came. And I wish smooth and fruitful running of the conference. I am sure that we'll have important presentations, new results, new ideas will be explained and developed, new conversations will be run around, and maybe new projects, new papers will appear after that. And taking the word for Lyudmil, let us do the second most important thing. Thank you.
Thank you, Peter. And now I would like to ask the President of the Bulgarian Okay, so I would like to ask the President of the Bulgarian Academy of Sciences to open the conference and to continue with the awarding ceremony. You know that our distinguished guest is Professor Kuntsevich. You know very well that Professor Kuntsevich is Fields Medal winner and winner of many other high and prestigious awards. So he is now foreign member of the Bulgarian Academy of Sciences, but without a diploma. So we have a special procedure for this. So please, Academic Revalski.
Thank you very much. Dear participants, I also would like to welcome you warmly here in Sofia. I'm happy to see so many people coming from abroad for this conference that was planned for 2 years ago, but due to the COVID stuff, we postponed it, and it was planned to mark the opening of the International Center for Mathematical Sciences, which was created at the Institute of Mathematics and Informatics of the Bulgarian Academy of Sciences. My name was mentioned several times here, but I would like to underline something very important, and this is this, the creation of this center was purely collective effort of the Bulgarian mathematicians, not only in Bulgaria, but also abroad. And which is very important, we received very strong support from many of our colleagues of Bulgarian mathematicians. Some of them are present here, like Maxim, who was one of our plenary speakers of the first conference, ICMS-Sofia, Professor Jean-Pierre Bourguignon, with whom we also discussed this. Some of them are not here, like Yuri Chinkel, who also gave a strong push for the creation of this center. And if I have to mention one name, really, this is the name of Ludmil. For me, it was clear. We have discussed with our colleagues. We started thinking about these things about 10 years ago. And the first initiative was the conference that was created. Then there was we created also a prize at the Institute of Mathematics and Informatics. And the center was the final step. It took a long time, but for me it was clear that without a person like Ludmil, such a center would not be able to function well, I mean from the point of view of the networking in the world. So really we all are very, very thankful to Ludmil for this extremely huge efforts he put in the creation and in the functioning now of the center. As you see, even with the COVID pandemic, the activities were very, very, very good, having in mind all these difficulties. And now, as Oleg mentioned, maybe this was just a warming process for the. Now, you will allow me to deliver to Maxim the diploma of foreign member of Bulgarian Academy of Sciences. We all know him very well, a world-known mathematician in the fields of algebraic geometry, algebraic topology, the mathematical aspects, geometric aspects of theoretical physics. So, but he's also friend of, I would say, Bulgarian mathematicians, because he is collaborating with several of our colleagues I see here. Professor Todorov, Professor Ludmil, also Tony probably is here, Pantev, and he was also supervisor of several Bulgarian postdoctoral students. And because of all this, our mathematical community proposed already maybe 3 years ago, almost 3 years ago, to the Assembly of corresponding members of the Bulgarian Academy of Sciences, the candidature of Professor Koncevic to be elected foreign member of the Bulgarian Academy of Sciences. And this happened almost 2 years ago, but without a diploma, probably you feel a little bit. So you allow me now to deliver him the diploma of foreign member. I will give, give me these switches, because for Maxim there is nothing here which he cannot understand. Because so there is also an English version of it. I will deliver you these switches in Bulgarian. So, congratulations. Дава този диплома на професор Максим Концевич Франция, избран от събранието на академиците за постоянен член на БАН. Okay, that is all. Thank you very much.
Thank you.
The lady wants to deliver. If you want to say a couple of words.
Yeah. First of all, I don't understand Bulgarian only as a Russian.
Yeah.
Close languages, but yesterday when I arrived at the airport, I said that I understand Bulgarian even more. Guichet, niveau, okay. Well, yeah. In fact, I'm very grateful to happy to be elected as a foreign member of the Bulgarian Academy of Sciences, and I have really singular large interaction with Bulgarian mathematicians all my mathematical life, starting with late Andrei Todorov, whose result was really fundamental in development of mirror symmetry, and then of course we have many friends and colleagues, Lyudmila, Ivan Todorov, Tony Pantyev, and we have Georg Dimitrov is now our student, and yeah, so it's really many. The place, so it's really feel kind of honorary Bulgarian. And also, this center, it's really wonderful idea, and I hope it will be a great future. Lyudmila told me it can host something like 4 IHSs. Okay, so it's really a huge center, and I hope it will have really great future. And thank you very much.
Thank you. Professor Koncevic. By the way, I had the opportunity also to participate when he was delivered the Fields Medal, but this was some years ago. And my colleagues asked me to open officially the conference. I think it was almost open until now, but anyway, I declare the conference open. And I don't know, before giving the floor to Maxim, maybe somebody else would like to say something?
Yeah.
Okay. Jean-Pierre Bourguignon.
Thank you very much for the invitation and for the opportunity to be here. I've been visiting Bulgaria a few times, and I have a number of Bulgarian friends. One Todorov is there, Lyudmila, and a few others. Vestislav, who is also in the audience. So I'm very pleased that the project finally went through. And I just want to say something about Maxime, because I've been the director of ITS for some years. And I think one of my first tasks when I became director was to convince Maxime to leave Berkeley and come to Bure. It was not so easy. And maybe something I can reveal is that our first appointment was in Pennsylvania station in New York, so that it would be discreet and nobody could see us. So that was an interesting beginning for this. But of course, having Maxime at IHS has been absolutely wonderful because of the mathematics he produces, but also the incredible contacts he has. I'm still coming to IHS regularly, and my office is almost across from his office. So I have these regular visits, and each time he's talking about something new. So it's a bit too much for me, but so thank you very much for your contribution to mathematics, which has been wonderful. And I hope we can develop further collaboration between IHS and ICMS. Of course, I'm not anymore the director for more than almost 10 years now, but I'm sure that collaboration can develop fruitfully. Thank you very much.
Finally, before giving the floor to Maxime, I give the floor to Professor Griffiths to say a couple of words. Okay.
So it's a great pleasure to be able to say a few words about, mathematical words about Maxime. I know of no other mathematician who has introduced more new areas into contemporary mathematics than has been the case for Maxime. Early on in his career, he proved the Witten conjecture. This is an amazing statement relating the moduli spaces of algebraic curves of all genera, lacing them together to give an expression which Maxime proves satisfies the codivectories, KDV equation. Just an amazing piece of work. In his paper for the International Congress, he formulated the concept of mirror symmetry, the form that is now is pervasive throughout mathematics, linking disparate subjects of algebraic geometry and symplectic geometry. Symplectic geometry is a Fukaya category. Fukaya is here with us today. With Yuri Manin, he introduced the foundations of Gromov-Witten invariance. In more recent times, he's opened up new areas in deformation quantization and motivic integration. Maxime, as you heard, has a very strong connection with the mathematics community here in Bulgaria, and I think we can look forward to further strong development of that connection in the years ahead. Thank you.
Please, Maxime, the floor is yours now.
Thank you.
I suppose that you know how to...
I hope so. Yeah, it's some plus minus. Yeah, okay.
Yeah, they will.
Give me a minute to...
Okay, yeah. Okay. Okay, yeah, so maybe I'll start first. Yeah, so thank you very much, and thank you for warm words. I will speak about some very recent work, very, very elementary, which was inspired by a preprint, in fact, a talk by Vladimir Kazakov, who is one of the founders of serious metrics models. He's now in France for many years, and he gave a talk on the conference at HS about maybe 2 months ago. I was very impressed by his talk, and this is a result you can read on archive. It's a result of Vladimir and his student Juan Zhang, which is impressed me very, very much, and I try to do something in this direction. So I'll start with a very classical, what's called Gaussian unitary ensemble and Wigner's semicircle law. What's all about? It's about random matrices and about random Hermitian matrices. Well, n will be capital N will be the size of my matrices. You can see the space of n by n Hermitian matrices. It's a real vector space of dimension n squared, and it has a quadratic form, trace of x squared over 2, and we multiply it by n. I explain why it's important. Multiply by n. So you get a Gaussian measure, it calculates the integral, you get this number. Okay, this really product of n square independent one-dimensional Gaussian integrals. And then if you divide by this number, you get Gaussian measure, get probability measure. Well, why it's important to put this n in the front of trace of x squared? And the reason that it's very simple calculation with deviations, that in this limit you see that all eigenvalues of matrix will have size of 1. The number goes not plus infinity, not to 0, it will be stay kind of reasonable eigenvalues. So we have some numbers of human size, not depending on n. Yeah, so that's a kind of right limit for matrix integrals. And now
for each integer we consider the following random variable. Consider k power of my matrix. It's still eigenvalues of size 1. There are n of them. We divide by n. We get mean value. We get some random number. And the story here goes that in this large n limit, this variable became not random, but just by some constant. It will not. It's going to deviate smaller and smaller than n goes to infinity. So I get this constant. What is this constant? Formally consider mean value of this variable. If it's close to the constant, it will be equal to this limiting value, and take a limit when size goes to infinity. Now, so one can easily calculate these things using Feynman rules, but I will not go into that. Now, so I get these constants, and because these variables became really just constant, not random, if you get a product of several of them, then it will be product of constants. Yeah, so you get some kind of like concentration of measure. So this, in certain senses, kind of measure will concentrate at one point. So the object will become not random. Yeah, so I have this property. Again, one can prove it formally. So I get the sequence of numbers which describe our behavior to large n. C0, C1. What we know? We know a few properties. First of all, if we have zeros power of matrix, we just get identity matrix, trace of identity n, divide by n, get 1. So it's really not random variable, just 1. So the C0 is 1. And then we get kind of the main hero of my talk. It will be this following quadratic identity. For any non-negative integer k, we take sum of I plus j equal to k plus 1. See I equals to j, you get ck plus 1. You can apply it for k equal to 0. You get empty sum, which is 0. And then you get c1 equal to 0. And so on. You can proceed further. Yeah, so I get this infinite sequence of quadratic identities which have different names in this physics, called loop equations, Ward identities, Schwingen-Dyson equations, all the same names for this identity, which I explain in a second. Yeah, so that's pure algebraic part of the story. You get sequence of numbers satisfying these identities, and from this you already see that you can uniquely solve this system. But let's ignore this for a moment. We have some kind of other properties. First, these numbers are real. And real, that's completely obvious because consider case power of Hermitian metric, it's Hermitian. So the trace is real and the mean value is real, so that's real numbers. And the final property is that if you make this semi-infinite matrix, C0, C1, C1, and so on these diagonals, that matrix will be non-negative definite. And then you can see just for pure reasoning, because what you do, consider some polynomial in matrix and multiply by Hermitian conjugate polynomial. Take trace of the guy, get non-negative number, and if you consider what is the mean value, then you see that this thing is non-negative, this number is non-negative, so it means that this infinite matrix is non-negative. It means that each final minor is non-negative definite. Yeah, so this so you get kind of algebraic features, two algebraic features, and two kind of real features and inequality. And this will be present in all other examples, as we will see. First I mentioned that this in this case for Gaussian unitary ensemble, you see that you have this just two algebraic equations, like initial value for the sequence and recursion. It defines it uniquely. And if you substitute, you get automatically odd powers get 0. It's clear from symmetry. But for even powers, you get Catalan numbers. That's the definition. And these numbers, I remind you, give this positive definite matrix. And what is positive definite matrix of such type? It's a moments of random variable on R. It's a famous Stiltes problem of moments. And these are moments of some probability distribution. And probability distribution is given by this formula. And here you see the square root of 4 minus t squared. So if you draw the graph, you get semicircle. It's exactly semicircle law of Wigner, famous semicircle of Wigner. So you see that without doing much of things except this concentration of measure, I think you derive semicircle law really from nothing. Except this, of course, you have these identities. What are these identities in general? So they call them loop equations, or you can use any other names. How to prove? It's actually extremely simple. For any non-negative integer, you consider a vector field on the space of Hermitian matrices given by the following formula. Its speed at any point x is k power of this matrix. We can write it in form like xk du dx, open matrix notations. So you get a real vector field space of matrices, and then you can use its integration by part. If you get a field in some measure, which is fast decaying in infinity, then integral of divergence of the field is equal to the integral of derivative with vector field of the exponent of this measure. It's just usual integration by parts. Not even the Stokes formula. It was basic calculation in mathematics. This is real total derivative is 0. Now we have to calculate two things. What is the divergence of this vector field, and what is the action of this field on this function of matrices. Again, it's very easy. You just write what is matrix. It's a bunch of matrix coefficients. You get n square variables, and you open, write everything in coordinates, and then calculate divergence. And it turns out to be this very neat quadratic expression in traces. And just you write everything in terms of matrix coefficients, and you see it immediately. And similarly, if you apply to to this trace of x squared over 2, I emit this factor n, which plays no role, you get trace of k plus 1. Yeah, so these are two abstract simple identities, and when you substitute, you get these word identities. Okay, so that's all about Gaussian unitary ensemble. Now let's do just real stuff, multi-matrix integrals. In fact, in theory of matrix integrals, there are too many models. One can write too many action functionals, and people study something like chain of matrices, like have matrix x1, x2, have some polynomial of x1, one of x2, and a trace of product x1, x2. But in general, one can do just anything. You consider several matrices, x1, x2, I didn't specify the number, some finite number of matrices, and the potential, which is linear combination of traces of products of some matrices. And what Kazakov and Jan considered in their paper, they wanted to study some kind of simplest example potential of two matrices. They want to have something positive, so take squares of some positive expressions. So take square matrix S1, square matrix 2, x1 to power 4, x2 to power 4, and then they add commutator. Oh, sorry, it was a very important term. We forgot to trace of x1 plus x2, because otherwise 6 will be decoupled. Yeah, so this print here, it was a trace of product. We should add with some constant. Yeah. And as one can see from the title of the paper, they consider this non-solvable model. And they kind of achieved, at least numerically, to solve it in this Laplacian limit, which is called planar limit. Actually, this main point of my talk, it's not really an unsolvable model. I think there's a good chance that it's solvable exactly in some kind of closed formula, which is not clear, but there are very good signs that even this kind of complicated expression has some nice features. Now, so you can, in general, consider many matrices, and sorry, you have traces of constants, so it's should be wrong. Here, these things are really coupled by this term. Okay, so in general, you write this any expression like this, and maybe put it in such form that it will be very big and positive at infinity, and then take a trace exponent n times this potential, and define again partition function, and get probability distribution. Yeah, so I assume, for example, this guy is real and goes to plus infinity at infinity, so it will be well defined. And the conjecture that like for Gaussian model, when you can calculate everything explicitly, there will be a nice limit when n goes to infinity because of this factor n in the front. It's called planar or 't Hooft limit. It's Gerard 't Hooft who proposed consider these things. Why it's called planar? Because if you do Feynman diagram expansion, because of metric symmetry, you expanded some kind of ribbon graphs, and in this limit, only planar graph will survive. Yeah, so the conjecture is that in such limit, if you get any expression, trace of any non-commutative monomial, there are many of them, and you have several matrices like this guy. You get the corresponding random variable, you only divide by n, it tends to a non-random constant. So you get just huge collection of constants to calculate these limits at infinity. As I heard from specialists in matrix model, it should be not difficult to prove in general, but as abstract question is still open, that you get this conformal limit. I will use it as an axiom. Yeah, it probably should be proven using some convexity tools in analysis. Not familiar with this story. So I will use this as, for me, it will be an axiom. I will derive everything for this planar limit picture. Yeah, okay. Yeah, so there are too many equations, and because there are too many potentials. So how we can formalize it? Yeah, first of all, our expressions in my matrices, I will write as words in the alphabet. By x1, x2. And for each word, so this planar limit says that for each word I have a constant, which in general complex number because these things will be not real variables, which will be limit of average value of this trace of the word with respect to this measure divided by partition function, so you get probability distribution. So this, so you get some complex number for each word, and again one can imitate properties of this, not a sequence, but really huge collection of numbers which we see in Gaussian model. First, for empty word, we get constant is equal to 1. Yeah, that's very simple but really basic identity. Then this constant depends only of word up to cyclic permutation. Take trace of x1, x2, x3, you put x3 in the form, you get the same trace. So it will be the same function to integrate. Yeah, so it depends only on cyclic permuted word. And then there will be loop equations. So it will be completely similar story. You consider some vector field on space of a collection of matrices, and derivative of each matrix is certain word or linear combination of words in these matrices. So you get many vector fields to play with. You substitute to this integration by part sync, you get certain quadratic identities, inhomogeneous quadratic identities, like for Gaussian integral. Then, yeah, this will be first three things will be algebraic part of my constraints. In the case of Gaussian integrals, I don't have second constraint because my versus was x. So there's no need to cyclic remove this factors. It will be the same. And then there will be again reality constraint, because if you consider any word, you read it backwards, you get opposite word, and then this matrix will be Hermitian conjugate. So the trace will be complex conjugate, so you get C of word will be complex conjugate to C of opposite word, you get some reality constraint. And then you get properties that something is positive semi-definite. Again, you use the same idea. You consider arbitrary non-commutative polynomial in words with complex coefficients multiplied by Hermitian conjugate. You get positive, non-negatively definite Hermitian matrix. This trace is non-negative, and integrals non-negative, and when you consider trace of negative, you get some quadratic expression lambda and lambda bar, which is some huge infinite matrix will be non-negatively definite. Okay, yeah, so one can really imitate the whole things. And what Kazakov and Jan studied. They write conditions, it's algebraic conditions, which I explained to you. This initial value for empty word to get 1, get cyclic invariance loop equation, And they get this positivity conditions, reality and positivity. And it seems that these conditions determined these numbers uniquely, at least in the examples they studied. How they proceeded, it's actually very interesting. They wrote words of maybe lengths up to 20 or 30, so that's some about maybe million of unknowns. Then we have, it should be computer work, and then get a system of inhomogeneous quadratic equations, system of inequalities, and then you want to, from this, deduce some estimate on the values of numbers. Say that they sit in some small intervals. And intervals are really small. At the end, I think you get something like 6-digit precisions for this 6. Just from nothing, just from standing of system equations and inequalities. Yeah, that's a bit, it's a really very hard calculation problem if you get quadratic equations. And they use the following trick, which is well known in numerical analysis. If you get quadratic constraints, you just get even more variables, consider quadratic expressions in new variables. And then these quadratic constraints you replace by some weaker conditions with some sort of rank 1 matrices, non-negative definite. So you reduce again to some huge system of linear inequalities, which is convex. And then there are fast tools in numerical analysis, and which gives you rigorous estimates. And the work, and I didn't show the plot, but you calculate larger words, and of course it takes more and more times, more and more hours for calculation, but then you get really concentration things. You say that this number like C of x1 square or whatever, concentrate to small intervals, which looks on naked eye to converge to just one point, so to a really unique solution of this inequalities. Yeah, but Kazakov asked in his lecture that these loop equations, there are so many of them, and he doesn't really know how to deal with them. And I started to think a little bit about this pure algebraic aspect. I forget about inequalities. Just as loop equations, we saw that they are really very powerful, and we saw that for Gaussian unitary ensembles, that's really enough of them. You don't need about this positivity at all. So first I'll try to think, what do you ignore about positivity? Can you reconstruct these numbers uniquely just for this infinite system of algebraic equations? It's, in principle, it could be possible, but it's actually, in some cases, very close to the truth, but let's explain why I was surprised by this. So I concentrated purely on algebraic part of the constraints, this loop equations and cyclic symmetry and so on. And if you think a little bit, you realize that there are more equations than variables. It's really over-determined system. Of course, it's infinite system, but it's kind of filtered. You get finite systems, finitely many equations, and each finite system has more equations than variables. Now, so it's really surprising that things has any solution at all. But maybe it has just one or some finite dimensional families. Who knows? Yeah, so I decided to look on it. Why there are more equations than variables? So variables are labeled by cyclic words, because when you make cyclic trace is the same. But equations correspond to these derivations. It's a derivative of metrics, it's some expression, and you're no longer allowed to make cyclic permutation. So you get non-cyclic words, and actually several non-cyclic words, because for each variable you have some derivative. And let's make a kind of like sample calculation. Suppose we have two matrices and degree of potential is 4, like in this, what to be the say non-solvable example we studied, like quartic non-commutative polynomial. Now consider variables of degree less than 100 and words of length of less than 100. Because the cyclic words and the cyclic group acts almost freely, you get words of length 100 will be roughly 2 to the power 100, number of words divided by 100 by action cyclic group, but words of length 99, 299. Okay, approximately it's 2 times this number, up to 1 plus small of 1. And 100 goes to infinity. But when you look at number of equations, this vector field, the derivative of my matrix should be polynomial of degree 100 minus 3, because when I apply potential, I have a derivative of potential, which is degree 3. and have two variables, and you make the sum, you get 2 to minus 1 to 2 power 100. And you see that it's of course 2 to power minus 2 to plus 1, what here 100 in denominator, here is no 100 in denominator. So it's definitely have much more equations than variables. What's going on? Why system of so determined system can have solutions? Yeah, so I was originally very surprised, but then I realized it's nothing to be surprised about. And in fact, I learned something for myself. It's just in many situations, mathematics one should expect when you have overdetermined system, should have many solutions. I explain you why. It's kind of some lessons which I learned from this algebraic game. Yeah. First of all, here one can develop some general formalism, which is kind of called resolutions, or complexes. It's some homological algebra. So we do these algebraic equations, and so we have what I call this potential. So first we consider words. Words form a basis of free associative algebra. So we forget about now matrix integrals, we do completely formal algebraic game. We get free associative algebra, and I consider cycle of B, it's quotient by space of all commutants. So it should be comma here. This is a finite linear combination of cyclic words, and potential is element of this cycle of B. Yeah, so you get free algebra and element in the quotient by commutators. And with such situation, one can define some differential graded associative algebra. It's called Ginzburg algebra, and for specialists, I have to say it's smooth in homological sense, three-dimensional Calabi-ODG algebra. But what is explicitly? We consider free algebra generated by odd number of variables, name variables x, kind of dual variables eta, and some extra variable epsilon. Now, so what is it? It's free associative algebra generated by this odd number of variables, 2 to the number of x's plus 1. And it will be graded by non-positive integers. So my original generators are put in degree 0, dual variables generators put in degree -1, and the last extra generator put in degree -2. And this algebra has is endowed with a differential which depends on the potential. So I have and differential will satisfy Leibniz rule, but with causal rule of sign. When I take, I use now parity of expressions. So in parity, this number of variables eta will be important when in Leibniz rule put differentials through etas. Yeah, so to define differential should define it on generators. Differential will be of degree +1. So differential of x size is 0 because there is no room. There's no elements of this algebra in degree +1. It's in positive degrees. Differential of eta will be what's called derivative of a cyclic word. Yeah, for the cyclic word, one can make derivative, get usual word of what you do. You have cyclic word, you have a letter, you remove your letter from some place, you get a string, and you take some of all possible strings. Yeah, so for example, you take, like, I don't know, x1, x1, x2, x1, x3, modulo commutators will be cyclic word, and take derivative by x1. There are 3 instances of x1. You just put each instance in the front by cyclic permutation and remove it. So you get this expression. Yeah, so it's very well known calculus in non-commutative algebra. You take derivative of cyclic words, you get usual words. And finally, I have add this variable epsilon of degree -2, whose differential should be something of degree -1, and it defines the sum of commutators of xi and eta I, of these dual variables. Y d square is equal to 0. You should check only on generator epsilon, and you have to check this identity. And it's a very beautiful identity in computer algebras, which holds always. And that's actually a reason to add this variable epsilon, because you have this for free, this identity, and we should kind of use it in making resolutions. And this algebra was introduced by Victor Ginsburg a long time ago and plays really essential role in reverse with potential, DT invariance, and completely different areas of mathematics, and like local Calabi-Yau varieties. But here it appears naturally in this problem with matrix integrals. Yeah, so I get this Ginsburg algebra. Yeah, so now I'll have a new. Sorry, it's also misprint. I have DC great community of social algebra. It's not co-algebra, so it's misprint here. See, namely, what I do. I have my Ginsburg algebra. I take cyclic words. It's again free algebra, but in grade it's graded. And because this is cyclic words in graded sense, so when I take commutators, I use causal rule of science. I get some complex of vector space and generate a symmetric algebra by this. Again, get symmetric algebra, so it's, sorry, it's not algebra, it's algebra. And mod out by one relation, name is the following. In the symmetric algebra, get unit element, get zero power, get unit element, canonical unit element symmetric algebra. But in the cyclic words, also have unit element coming from unit in algebra. And we say mod out by relations that these two units are the same. It's exactly correspond to the axiom that this limit C of empty vert is 1. It records it's the most simple axiom. So elements of cyclic words we can write because to understand that origin, this trace of depends on the cyclic word, but trace of words, but now in this letters of 3 types. And now this algebra has a differential, and it's kind of center part of this formalism. And the differential is the following: on the space of, let's ignore this relation; it's really almost nothing. On this on space of cyclic words, this is a differential induced by differential of algebra because it's construction taken by portion. It's natural construction, so if you take differential, it goes to differential. And I'll add a second term which is responsible for divergence. You remember that when I calculated divergence of vector field on matrices, I get product of two traces, and it's kind of like abstraction of the story. So divergence will be a map from space of cyclic words to symmetric square of degree +1. And what is it? It's kind of formal procedure. You have cyclic word, and in this cyclic word you look on pairs of conjugate variables, xi and eta in two places. You remove these two cyclic, two matching variables, and you get just two strings, and close the strings to cycles and get two traces. So it will be the formula. If you get one matching variable, some word, and xi, another matching variables, another word, you just take trace of this component times trace of another component, and the sum of all possible other matchings. Yeah, this is something which is look familiar in the subject, writing cyclic words and variables and dual variables. A very long time ago, I introduced some Poisson bracket, but it's kind of dual operation. It's not. It's called brace. Necklace bracket, something like this. It's a different operation. Take two cyclic words, find matching variable in the first word to another, and combine them to one cyclic word. This is another guy, which also appeared in work of Tradler, and it's kind of mysterious operations in both ways, and so one can say that it's simultaneously in Lie algebra and Lie coalgebra, so you get Lie bialgebra. But here I use only this second, not necklace bracket, this divergence story. And this is the definition. So I described you some kind of abstract construction. We have this Ginsburg algebra, get cyclic words of the quotient by commutants and cyclic algebra, make symmetric algebra, make this crazy differential, maybe divide by some ideal. Yeah. how it's related to our original question. All this algebraic part of this story which you study, this unit constraint, cyclic invariance loop equations, it's equivalent to this just way to can be repackaged in the following question. Find a homomorphism from zero cohomology of this commutative algebra to complex numbers. Yeah, so it's all the equations will be just studying a spectrum of some commutative algebra, which could be big, I don't know, it's countable dimension, nobody knows this probably. Yeah, so if you omit this unit constraint, which plays a really minor role here, then this commutative DG algebra, it's Chevalier-Ellenberg complex of DG Lie coalgebra. This bracket gives you a structure of kind of Lie coalgebra. Dual space will be Lie algebra, and if you consider this, it's Lie cohomology with continuous topology will be exactly this complex. Yeah, it's kind of some algebraic repackaging, but with the same equation. And the whole story really works only in this planar limit, n equal to infinity. One can try to see that integration by parts one can do in finite dimensions and get something. But here in finite dimension, we get some parasitic term which destroys the structure of this DG Lie algebra. Namely, if you have product of two traces and some vector field, then you consider divergence gets extra term, which appears with coefficients 1 over n cube, and then the limit disappears. Yeah, so it's really about this story. It's really only about this planar limit, which is hypothetical, but for me it's an axiom. Yeah, there was actually a recent paper by several mathematical physicists, Williams, Ninalian, and I forgot the name. They studied in very, very great details Gaussian ensemble for finite n and these algebraic structures, brackets, co-brackets. But my story is kind of much simpler. It goes only for planar limit. Yeah, actually, it was really funny. I gave a talk about maybe months ago on this subject, on some seminar on mathematical physics organized by Joel Lebovitz, and then 2 days later somebody told me, oh, you know, there's a paper on archive and they cited you. I looked on this paper by Zenalian and company. They cited me lavishly, yeah, this brackets and so on. And I thought, oh, how on? I just gave a talk, and 2 days later the paper appears, which is almost the same subject. But turns out it's a complete coincidence. They worked on it for several months. And, it's a bit different story. Yeah, okay. So now I go to some experimental results. Yeah, here one can have kind of very explicit differentials. One can make calculations and again ask computer to do heavy work. So what I try to just take some polynomial of some small degree, at least 3, because quadratic story is reduced to Gaussian ensemble, and at least 2 non-commutative variables was in one variable. It's little, it's kind of one matrix model. It's already by loop equations essentially solvable without any positivity constraint. Yeah. So I got this natural class of potentials to explore, and now I have this infinite number of equations and variables. I should kind of bound them and get finitely many equations and finitely many variables. And for this, I introduced some filtration. So on my Ginzburg algebra has 3 types of generators: X, original words, and etas, kind of dual things, and epsilon, formal guy. And I associated weights of X equal to 1, eta to d minus 1, epsilon to d. Why I introduce this weights? Exactly because this differential preserve doesn't increase the weights. It's the most natural thing to do. Yeah, so I get increasing filtration algebra, and then all associated objects like cyclic words and symmetric algebra cyclic words by finite dimensional subspaces. These are the differential. So there are finite dimensional complexes, and then I can really do calculation on computer. And yeah, first of all, if you get finite dimensional complex, what you do, you calculate its Euler characteristic. Yeah, it gives you some idea how large cohomology could be. If it's zero, cohomology vanishes everywhere. It implies characteristic zero, so it implies that that's a non-trivial cohomology. And the geometric function for Euler characteristic, it's very easy because you just ignore differential, just consider parity of complexes, and then you get 1 over certain polynomial. As a expanded series, the polynomial is the following one. You get 1 minus k times t, because you get k generators of degree 1 plus k to power d minus 1, because k odd generators of degree d minus 1 and minus t to power d, you get 1 even generator of degree d. You get 1 over this not very interesting polynomial. Okay, which controls you roughly this Euler characteristics. And this computer experience shows that there are really 3 different scenarios when can, like in many other areas of elliptic, parabolic, and hyperbolic case. So the elliptic case here in my equations is only 1. When I get 2 matrices and cubic potential. It's actually not physical equation because I want kind of like positive functional space of matrix, and trace of cube is not positive. Yeah, so it's completely formal algebraic game, but still it's very interesting to study. And in this case, something really funny happens. So for generic potential, algebra you consider kind of like finite piece of iterations. You cannot predict cohomology just from Euler characteristics. They're concentrated in several degrees. And it turns out they're only in even negative degrees. And in fact, that if you go to this infinite, if you don't get any restriction to filtration, still get finite dimensional cohomology, and all rank of cohomology will be 6, 0, 6, 0, 6, 0, and so on. Yeah, so this happens. It's kind of a really nice periodic case. And for the cyclic words, you get similar story. Actually, it's a bit more complicated. Dimension of h0 is 4. I don't know why. Okay, dimension of h minus 2 seems to be infinite. It seems growing when you increase filtration to minus 4 and so on. It's really very hard to calculate. I cannot say. I calculate maybe up to weight, I don't know, 11. Then I need more RAM than I have in my computer, and it really goes very, very fast, this calculation, and I have to stop at some point. And odd cohomology again for cyclic words are 0. Okay, so it's a very important thing that it's, for example, negative h minus 1 seems to be 0 cyclic words. What's the reason of this? Because it implies that if you consider commutative algebra, it also have nothing in minus 1, and h0 will be symmetric algebra in 3 variables. Not 4 variables because we get the unity constraint. So that means that for these 6, which would be interesting models, you have so many variables that essentially you get only 3 unknowns, not infinitely many unknowns, just 3 numbers. I don't know, it makes no sense to ask here whether it's good algebraic numbers or transcendental numbers, but just 3 numbers which determine everything. So it's essentially like one matrix model. But unfortunately, there's no good equation to study the limit. There are 2 parabolic cases when, and one is exactly this physical, it's exactly the case with Kazakov and Zhang study. They get a quartic polynomial in 2 matrices, and another again non-physical, actually cubic in 3 matrices. These are very similar examples. In both cases, for the generic potential, a different story happens. Unlike this elliptic case, this algebra will have cohomology only in 0 degree. And that means that you can consider finite term filtrations have terms cohomology in 0 degree, so you can call homology by Euler characteristic. And the growth of the thing has a cubic growth. So it looks like polynomials in 3 variables in both cases by filtration weight. But when you consider cyclic words, this h0 will be quotient by commutant. It has a linear growth. How it happens? In fact, this algebra h0 of a, in some simple example, when potential is x, y, z minus z, y, x, there will be polynomials in 3 variables. And if you derm potential a little bit, you get some non-computed deformation of the algebra. So it looks like you have Poisson bracket in 3-dimensional space. And then the center of Poisson bracket will be only Casimirs depend on one parameter, so it means that this thing will have linear growth. And slopes depends on these two cases, 7, 4, 8 over 3. And again, h minus 1 vanishes. It's again lucky case. And we get polynomial algebra in infinitely many variables labeled by integers. It's infinitely generic algebra, but generators are kind of things which are now we're not afraid in mathematical physics to label like 1, 2, 3, not by words, not by expansion number, but it's something reasonable. It's like free fermions in conformal field theory. So it seems that pieces work all the time. So for me, it's really the case which they call non-integrable. It's actually integrable. Yeah, so because the growth is so small, and so it should be some hidden structure here. Yeah, and there are hyperbolic cases. It's kind of similar story. Homology of algebra sits in degree 0, and for cyclic words you don't have autohomology. We still have h minus 2, which I don't know how to explain. But this thing has exponential growth. It's kind of out of the reach for the modern understanding. And what is the lesson? Well, this is kind of a very simple general lesson. So we see that suppose you get some complex of vector spaces, of finite dimensional spaces. And the complex may depend on some parameter, and you look at like special values, control parameters, deform a little bit. And let's call it complex stable if for each I cohomology in degree I is 0 or in degree I minus plus 1, 0, or both of them. So you don't have cohomology in 2 adjacent degrees. It's kind of typical what you expect for differential. If it's unstable, it can deform a little bit the differential and cohomology became smaller. But if they have the separations, that's no non-zero cohomology in adjacent places, then this thing is stable in the sense that if you change a little bit the complex, the cohomology will have the same dimensions. And yeah, first of all, since that for generic potentials, in all cases which I considered elliptic, parabolic, hyperbolic, the cohomology of the cycle complex are all concentrated in even degrees, so they're automatically stable. And then the same is true cohomology of symmetric algebra, they're also concentrated in even degrees. Yeah, so and then you see that zero cohomology with symmetric algebra. Yeah, it's not arbitrary commutative algebra, it's really polynomial algebra. But in general, if you had some complex like this cyclic complex, and it depends on some parameters, the coefficients of your potential, you cannot say anything about cohomology based on early characteristics. If the cohomology not concentrated in one degree, it's how the kind of the fate decide for you. So one class of questions, cohomology will be only in degree 0, from degree 0 minus 2, or so forth, and so on. You cannot really predict a priori. It will be kind of open condition for your differential. Yeah, and then you see that the dimension of zero cohomology could be pretty large. Even naively, you look at have overdetermined system, and I think it's a very general mechanism, and many questions in whatever algebra, differential geometry. Like I don't know, consider the question: what is a Lie group in a formal neighborhood of a point? You write n coordinates. You consider product. You get product at something like n function of 2n variables. You make Taylor expansion. You get many numbers. And you consider equation for the associativity. You get n function of n cube variables. 3n variables. Get much more number of variables, equations and variables. How it happens that Lie groups exist at all? Yeah, it's, if you try to look at formula in terms of expansion, you get so overdetermined systems that it looks impossible object. But we know because this notion of associativity has a nice resolution, this notion of A infinity, whatever, this big resolution explains that in principle, cohomology could be everywhere. It could be even big cohomology in degree 0 in some kind of stable reasons. So that's why many things in mathematics exist here. Okay, thank you.
Oh, thank you, Maxime, for a very interesting talk. I think we have time for questions, comments.
Yeah, if h minus 1 you have vanishing of the cyclic word, which happens in all examples for generic potential. For non-generic, it's not the case. Then we get this polynomial algebra. By the way, I want to say that it's, if one try to make analogy with commutative case, when we get, let's say, polynomial in commutative variables and try to calculate an integral of exponent minus polynomial by parts and call it homology. That's things which people do in singularity theory also from the very beginning, and get usually sum of Milnor numbers, and typically if you have non-inhomogeneous polynomial, homogeneous polynomial gets still homology 0 degree in commutative case. But here in the non-commutative case, it's completely opposite story. For this parabolic and elliptic cases, when I put just homogeneous potential, I get many homology degree, -1, -2, so the picture is very unclear. But for non-homogeneous potential, things stabilizes and became really separated. Yeah?
The one difficulty you mentioned with Lie groups, is it similar to the difficulty of obtaining Kac-Moody groups from Kac-Moody algebra?
No. You see, it's kind of different. Of course, we have Lie series. Lie groups are equivalent, locally Lie groups are equivalent to Lie algebras, but for Lie algebras we also get overdetermined system equations, which is again explained because we have natural deformation complex. No, it has nothing to do with. It's really calculation form power series.
Are there some hidden symmetries or conserved quantities going on?
Yes, it's this resolutions about relations between relations. In fact, I want to mention some kind of example which should be close to many people's interest. It's this famous equation, and it's called Einstein equation, this, let's say, this cosmological constant 0. And if you look on this equation, it's something interesting goes on. You start with symmetric, which is symmetric tensor on your manifold. It's your variables and equations. It's vanishing of Ricci tensor, which is another symmetric tensor on your manifold. It looks like a number of variables equal to number of equations. You should have kind of isolated solutions. But in fact, it's not the case because if you rescale your metric by constant, Ricci tensor doesn't change. So you have a map from metrics up to constant to symmetric tensors. And then symbol is kind of Laplace operator, and you see that it has index -1. So you get informally one more equations and variables. And then the conclusion that Ricci flat manifold shouldn't exist. Because you have really overdetermined system. And there's no natural resolution here. And the fact that Ricci flat manifolds don't really exist, if they exist, there is some different reason. You cannot, they're not really stable. You cannot solve some approximation computer because of this really overdetermined system. And all examples of Ricci flat manifolds have special holonomy. When you get special holonomy, you get some resolutions, you get complexes, and the homology could be set here, there, as you like. So like Todorov theorem, later great Todorov theorem, about smoothness molecular Calabi-Yau. It's based on existence of extra structure, then gives you resolutions, and then you get all story. But Einstein equation, it has no hidden structure. That's it.
If there are no more questions, comments, I'd like to thank Maxime for a beautiful talk. You probably know the correspondence between Einstein and Descartes about overdetermined.
Cette semaine.
I guess
something separate from this topic or
That's different. Една женица с синя рокля, която се занимавахме с фактурата с нея, дали все още е тук или
Let's start with the afternoon session. Well, it is a great pleasure to introduce Professor Philip Griffiths from IAS in slow introduction. And he'll be speaking today about Hodge theory, what is it, and how can it be used in algebraic geometry. Philip?
Thank you, Ernesto. It was suggested that I try to give a talk for a general mathematical audience, and I've tried to do so, as you will see. This talk will be centered around complex analysis, elementary complex analysis, and the real mathematical content will be essentially one complex variable and how it appears in at least the beginnings of Hodge theory. So to begin, the origin of Hodge theory in some ways began with calculus, with the study of integrals of algebraic functions. In the 18th century, a number of mathematicians were concerned with integrals of this kind. So this is the integral of a rational function where y is so-called algebraic function. Typically, an integral, a hyperelliptic integral it's called, would involve the square root. And that's the algebraic equation. These arise in many areas of mathematics, and as I said, in the 18th century they were of much concern. If the degree of a polynomial is 2 or less, it's an elementary integral. It can be evaluated in terms of elementary functions. But as soon as the degree becomes higher, it no longer can be evaluated in this way. These integrals arose, for example, in terms of parameterizing ellipses by R point. So for degree p bigger than or equal to 3, that's not the case. And this is the typical picture of the cubic algebraic curve that arises from the from trying to evaluate the integral of the algebraic function involving the cube root of a polynomial. At the turn of the century, Abel wrote a very famous paper in which there were two basic ideas. His first idea was what's now called an abelian sum. So instead of looking just at the simple integral, you look at the solutions of a pair of algebraic equations, your polynomial equation and another polynomial equation with a rational parameter. So typically the rational, the G is just a family of lines, and this would be the picture that you would get. Abel's theorem is very simple to state. The integral here is an elementary function of t. So you cannot evaluate the individual integrals, but you can evaluate the sum. And it's expressible in terms of logs and sines and cosines. The second idea was inversion. Instead of trying to evaluate the integral, invert it, define x and y to be the function of u that gives you the value of the integral. For example, sine and cosine. The sine and cosine are periodic. So let me say just a word about that. If you integrate from here to here along the red line, or you can integrate on the green curve where you go around the slit. And here I've slit the complex plane between -1 and +1, so you can choose a single value of the square root of x squared plus y squared, or x squared minus 1 in the complement, right? And you have the same upper limits for the integral. So if you think about it, what it means is that those functions that are defined by inversion are periodic. Okay. Or if you take the cubic curve, you have two slits in the plane. This cubic curve has one point at infinity. That's a so-called branch point. And you can integrate either around the purple curve to get from here to here, or you can cross the slit, change from one value of the square root to the other, go back to the other slit and change back. So it's a doubly periodic function that's defined by inversion of the elliptic integral. Okay. So Abel's theorem then translates into addition theorems. For example, the sine, usual one for the sine, and for the cubic one you get the Weierstrass p function, and for example that tells you p of 2x is a rational function of p and p prime. Here, by the way, both cases the integral is dx over y, so when you differentiate the integral, what you find is that the second coordinate's the derivative of the first. Okay. So this is just elementary one complex variable. The next stage in the development of Hodge theory came with Riemann, the concept of a Riemann surface. Riemann surface is a one-dimensional compact complex manifold. Has a local holomorphic coordinate. So typically, the easiest one, of course, is the Riemann sphere, with the coordinate at infinity being 1 over the coordinate on the plane, or the complex torus, the plane modulo a lattice. We'll come back to that one. Okay. On a Riemann surface, you have a concept of analytic and meromorphic functions locally. Same for differentials, holomorphic and meromorphic differentials. And so typically the integrand in these integrals of algebraic functions are a meromorphic differential on a Riemann surface. This was Riemann's concept. If you change coordinate around the point at infinity, then from this expression you find that the differential that's on the earlier slides, this differential here, is actually holomorphic on the whole Riemann surface, meaning the integral is finite if and only if the degree of the denominator is bounded by that numerator. So this doesn't happen when you have a quadratic polynomial. But as soon as you get a cubic or higher, it begins to happen. So there's a big change that occurs with higher degree, that the Riemann surface of the algebraic function actually admits holomorphic, everywhere holomorphic differentials. Okay. These were called classically integrals of the first kind. Modern terminology is that these are the global sections of the cotangent sheaf. In fact, Abel defined the genus of an algebraic curve to be the dimension of the space of integrals of the first kind. This is his definition. Okay. Riemann then connected that to topology. The first homology or cohomology of the Riemann surface has dimension twice the genus, where the genus is just the number of linearly independent differentials of the first kind. So here you have a connection between analysis and topology. That's really the first step in modern Hodge theory. Riemann actually showed on this cohomology that there's a bilinear form coming from what's now called the cup product in cohomology. I just wrote down the two inequalities. Well, there's an equality and an inequality. And modern terminology then is that the first cohomology of this Riemann surface gives a point in the space of Hodge structures of weight 1. The space of Hodge structures of weight 1 are points in the projective line. Okay. So these are the two integrals, the integrals around the two homology bases in the Riemann surface. And the imaginary part's positive, meaning on the projective line, the Riemann sphere, you're sitting in the upper half plane. Okay. So this was just very sketchily what the beginning of modern Hodge theory with Riemann. This was extended in the second half of the 19th century by Picard especially, also Poincaré. They considered single and double integrals. Okay, so you have now no longer an algebraic curve, but you have something of complex dimension 2, an algebraic surface. The definition of integrals of the first kind was as before, either for differentials of degree 1 or degree 2. And actually Picard established this decomposition, the Hodge decomposition, on H1. He deduced it from that on the Riemann surface you get just by holding one coordinate constant. Okay. When you come to H2, from the cohomology, you have these differentials that are everywhere that are of the first kind. That is, that their local integrals are everywhere finite, no poles. Okay. So you have these and their conjugates. So here's that space and the conjugates. But there was a missing piece, which Picard also found. Namely, if you have an algebraic surface, on that surface you have algebraic curves. So here's a quadric with a line on it. And locally, the curve, algebraic curve, is given by one analytic equation. Z and W are the local holomorphic coordinates on the surface. Have one equation, so that just trivially restricts to 0 on an algebraic curve. So this gives you, its homology class gives you something here. And it's non-trivial for topological reasons. Also importantly, Picard proved that if you look in the third homology and you take your surface, it's a 4-dimensional real manifold, intersect it with a hyperplane, okay, that's a real dimension 2, you go from third homology to first homology. He proved this is an isomorphism. The next stage in the development of Hodge theory was in the early part of the 20th century. Lefschetz, using methods of Picard, we're using them with great originality, the so-called Lefschetz pencil method. He proved that the odd Betti numbers are even. That already follows for algebraic surfaces from this, because this space here is the conjugate of this, and H3 is the same as H1 as Betti number. Lefschetz proved in general the odd Betti numbers are even, and that the even Betti numbers are at least 1. We saw that here because we've exhibited a non-trivial class in the second homology, and that generalizes. So he extended Picard's results to general dimension. Also, the Picard result that I mentioned from H3 to H1, here Lefschetz formulated it as intersecting with a hyperplane. The homology above the middle intersect enough times to go symmetrically to the homology below the middle. He claimed that was an isomorphism. And his proof of this was incomplete. Picard's proof, interestingly, was okay. It depended on special features of algebraic surfaces. But in higher dimensions, the Lefschetz argument was incomplete. That led to Hodge, and the definition of really the formulation of what a Hodge structure on cohomology is. I just reviewed that here so we have the terms. The cohomology of any manifold, particularly a complex manifold, is given by de Rhams' theorem as differential forms that are closed modulo those that are exact. Interestingly, Picard and Poincaré were using de Rhams' theorem. Well, first they were using homology just as it was being invented by Poincaré, and they were using de Rhams' theorem as if this was somehow clear. They never really formulated it, they just used it. Okay. The actual statement came in the early part of the 20th century. On the differential forms, you have local coordinates z, and they're conjugates, and so you can break up a differential form into the number of dz's and dz bars. That's called the type. And that led this decomposition on differential forms gave on cohomology the Hodge decomposition. So that's a Hodge structure. And the connection with algebraic geometry, for those of you who know the notation, it just says the cohomology, that the HPQ part of the Hodge decomposition is the Qth cohomology of the whole sheaf of holomorphic P forms. So that filled in what was missing in Picard. These are the 1-1 forms. Hodge also proved, for example, that holomorphic differentials are closed and never exact, things like that. So this is the general definition of a Hodge structure. The vector space that you think of as the cohomology, a filtration on the vector space that is gotten from the Hodge decomposition and reformulates the Hodge decomposition by these conditions. Hodge structures in cohomology have strong implication. You recover Lefschetz's theorem because the odd dimensional space is the direct sum of a vector space and its conjugate. Going much further, if you have a holomorphic vibration, I'll talk about this in a minute, the Leray spectral sequence degenerates at E2. So you don't have the complexities that you get in topology from vibrations. And if it's simply connected, then the homotopy type, the rational homotopy type, is determined by the cohomology ring. Again, that's something you don't have in topology. You have Massey products, things like that, that give the complexity of the homotopy type once you have the cohomology ring. And finally, Hodge proved hard Lefschetz. Okay, so that was the first proof. Interestingly, Hodge proved hard Lefschetz, but Hodge didn't prove Hodge's theorem. Hodge's theorem says that the cohomology, the Durand cohomology, is represented by harmonic forms. And they did not have the analytic tools when he was doing this to give a rigorous proof that you could represent cohomology isomorphically by a Riemannian manifold compact by harmonic forms. The first proof I'm aware of that was a seminar given at the Institute for Advanced Study in the early 40s by Hermann Weil, going over Hodge's book, and he spotted that the proof was incomplete, said we need to fix that, so he proved what's now called Weil's lemma, which is the statement that a weak solution of an elliptic equation is actually strong, smooth. The next stage in the development of the formalism is from Deligne, extending the Hodge structure from a smooth, compact algebraic variety, or Kähler manifold actually, to singular ones. And it's given by a mixed Hodge structure, a pair of filtrations where you have a Hodge filtration and a weight filtration. This is the formal definition. And one way to think of it is that a singular variety is stratified. You can desingularize the stratification, the strata. Those all have Hodge structures. So somehow through homological mechanism, you can look for something like a Hodge structure on the total space. The weight filtration tells you, in some sense, for a complete variety, the dimension of the strata on which the cohomology is supported. One linear algebra property of any vector space with a pair of filtrations satisfying these, it's an amazing lemma, is that morphisms, things that preserve each filtration, are actually strict. If you blend in one filtration level, you actually come from that to begin with. That has all sorts of implications when you actually use it in studying the topology of algebraic varieties. Going back to the spectral sequence of a fibration, this is the D2 map. It goes from something like this to something like this, and you notice this adds up to something different. If this is a morphism of Hodge structures, it's got to be 0. So that's the essence of the argument about the degeneration of the Leray spectral sequence. Hodge theory has many aspects, the topology of algebraic varieties that I mentioned, analysis, both complex analysis and PDEs, and the geometry of algebraic varieties, for example, moduli. The usual applications are the ones that arise in topology. Whenever you're studying algebraic varieties and maps between them, you want to look at the corresponding maps on homology and cohomology. Those have very strong linear algebra properties. And those are, I think, in some ways, the most frequent uses of Hodge theory. Okay. On the other hand, I want to illustrate a different use of Hodge theory. It's a famous problem of Shafarevich.
And so the approach to this problem was initiated by, well, Kolar, the topological side of it, but the Hodge theoretic side by Gatsarkov. And so I thought it would be appropriate to mention here something that actually originated from mathematics from Bulgaria. So let me just talk a bit about the Shafarevich problem and that result. So I want to take the question, can Hodge theory be used to construct something interesting analytic, for example, meromorphic functions? So here I'll go back into the classical pages, go back to the cubic curve in Weierstrass form, the elliptic integral, and it has two periods. This differential has two periods, and it defines local analytic functions, just inverting the integral. Okay. Abel's theorem, remember Abel's theorem said that the abelian sum is a rational function. You can actually evaluate that rational function in examples. And what you get, for example, if you take a cubic curve and you take a flex tangent and perturb it a little bit so that you have 3 points of intersection, this is what Abel's theorem translates into. So the sum of those integrals to those 3 points of intersection is constant. So you can use that, for example, to show that the original functions defined locally can be defined in a larger disk. I mentioned that when you can double that the Weierstrass function of 2u can be expressed in terms of Weierstrass and its derivative at u. This gives you a way of doubling the domain of definition of this meromorphic function. And you just extend it then to be an entire meromorphic function in the whole plane. So integrating that holomorphic differential on this cubic curve, Riemann surface of genus 1, generates the Weierstrass function, okay, suitably interpreted, and you can say more that this is the Riemann second bilinear relation. The ratio of the periods is positive. I'll come back to that in the latter part of the talk. And it gives the parameterization of the cubic curve by an elliptic functions, Weierstrass and its derivative. So just as you parameterize the circle by sine and cosine, you now parameterize the cubic by Weierstrass and its derivative by inverting the elliptic integral. So a simple consequence of that is that this function gives a holomorphic function on the universal cover. And that's a trivial consequence of that. Much less trivial is Luz-Mills' theorem. If you have a smooth projective variety for which the fundamental group is nilpotent, take a basis for the holomorphic differentials, okay, integrate them on the universal cover, and the theorem is that the image, when you do this, is a Stein variety. It's a very special type of non-compact analytic variety. And moreover, you can say what is lost when you take this map. It's the inverse image up in the universal cover of those subvarieties for which the first homology becomes trivial in the total space. Okay. You're integrating these differentials, you expect you don't get anything interesting unless you have non-trivial periods. And that's what this amounts to saying. So a general question is, how does one construct functions on the universal cover of a smooth variety? For pi1 x nilpotent, there's this result. So going back to the classical case, the other extreme is where the fundamental group is very non-abelian. So here I'm going to take the case of a non-compact variety, P1 minus 4 points. I should have put infinity here. Okay. So you take the Riemann sphere, take out 0, 1, infinity, and now have a variable point t. Oops. You have this cubic curve, and we discussed the integral, the ratio of the integrals. That's a locally defined analytic function on x. The differential is everywhere regular, and if the integrals, the periods depend holomorphically on the parameter just by, it's obvious just looking at the formulas. So you get a locally defined analytic function on x. Analytic continuation gives you a holomorphic map from the universal cover to the upper half plane. Remember I mentioned that the ratio of the periods is a point in the upper half plane sitting on the Riemann sphere. So in this way we have not only an analytic function, a bounded analytic function if you want, on the universal cover. And we were thinking of the space of Hodge structures of weight 1 and dimension 2, the H1 has dimension 2, as points in the upper half plane sitting on P1. Analytic continuation of the period ratio gives you a representation of the fundamental group of a complement into SL2. And you get this diagram. The universal cover maps to the upper half plane, X maps to the quotient. And of course, the one corollary of this construction, as you all have seen from elementary complex analysis, is Picard's theorem, an entire meromorphic function omitting those 3 points is constant. Okay, just because any bounded analytic function, entire function is constant. What is important though in this diagram is this picture on the right. That generalizes. The space of Hodge structures of a given type is a homogeneous complex manifold. So here think of upper half plane, but now you have all Hodge structures of a particular weight and a given type. That's acted on by the obvious linear group. Okay, preserves acting on the vector space. The isotropic group of a fixed Hodge structure is compact, because if you look in the Hodge decomposition, you have positive, definite bilinear forms occurring in the spaces against their conjugates. So it's actually a product of unitary groups, and in the odd case, an orthogonal group in the middle. Okay? So that's the space of Hodge structures of a given type. One may try to construct variations given by holomorphic maps. And this would be the monodromy representation. So for example, if you have a family of smooth algebraic varieties parameterized by x, okay, like when we had the Riemann sphere minus 3 points, and x is just the branch cover of the Riemann sphere branched on 0, 1, t, and infinity. So it's some generalization of that. Take the Hodge structure for each t. Okay? That's going to give you such a map. Now, if you have an arbitrary variety, you don't know that you have such families. Okay? There's an existence theorem here, very informally stated, which is due to Carlos Simpson, who's also been involved in the partnership between the Math Institute here in Miami. Says that when X is compact, if it has a faithful linear representation, then it has a variation of Hodge structure. Okay. So it's an existence theorem. So it's a beautiful existence theorem. It involves solving a nonlinear Yang-Mills type equation. That's the good news. The bad news is that in general, this D will have no non-constant analytic functions on it. These are much studied in homogeneous complex manifold theory. A lot is known about them. And the ones that arise in Hodge theory, except for very special ones, will have no non-constant analytic functions. So you can't work the previous argument. Okay? But there's good news. So the bad news is there's no non-constant analytic function. The good news is that there's a compact dual. And the way to think of that is if you think of filtrations on a vector space satisfying two bilinear relations. The first is inequality, the second is inequality. Drop the inequality, you just have equalities. That gives you a homogeneous, rational homogeneous variety, projective variety, okay? Like the Riemann sphere. It has a volume form, and you can look at the ratio of the volume forms. Here it is for the Riemann sphere, and now I'm using the unit disk with the coordinate zeta. This is the ratio of the volume forms. It's a function, and that function is an exhaustion function. That is, it goes to infinity at the boundary because this thing, denominator, goes to 0. And it's known that it's plurisubharmonic. So in complex analysis, if you want to construct analytic functions, you look for plurisubharmonic exhaustion functions. This is, and it's exactly those complex manifolds that have such plurisubharmonic exhaustion functions that are Stein varieties. So now we're in good shape, and the final result that comes out here, and two of the authors of this are with us here at this meeting, gives the extension, gives the analog of the theorem of Katsarkov with pi1 nilpotent in the semi-simple case. And it does use Hodge theory then in two forms to construct analytic functions. Okay? So this is one use of Hodge theory. I'm going to go back now and talk a little bit about something that's, I think, quite well known to many of you. It's the use of Hodge theory in topology. But it's not the ones that I listed before that go back to Hodge. This deals with a family of algebraic varieties over the disk, which are smooth except over the origin where they acquire singularity. So think of the family of cubic curves where the parameter t now hits 0, 1, or infinity. So some singularity appears. What happens topologically when that singularity appears? Suppose you go around the singularity and follow your homology around. What can you say about that? Okay. So that's the monodromy operator. And the result is that the monodromy operator, this is the Jordan normal form, the semi-simple and unipotent part. And the result is that the eigenvalues are roots of unity, and the index of nilpotency is bounded in this way. So what I want to do now is go back to the family of cubic curves and prove this theorem using one complex variable methods, but the argument will work in general. So we're back to the same old one parameter family of cubic curves, except over the origin t is now 0, 1, or infinity. And the complex analysis tool that comes in is the so-called Schwartz lemma. The classical version of Schwartz lemma is an analytic function mapping the disk to its disk. The origin to the origin is bounded in this way. Or if you phrase that geometrically, what it says is that if you use the Poincare metric on the disk, so that's the hyperbolic metric on the unit disk, then the Schwartz lemma says that it's distance decreasing. Alford's generalization said that if you have any metric on the disk whose Gauss curvature is negative, then you still have the distance decreasing property. So here, complex analysis and differential geometry are going to come in to be used using Hodge theory to prove a topological result. So from the above, we have this picture. The puncture disk has its universal cover, the upper half plane. The ratio of the periods gives this map. So I'm just looking now at the Hodge structure of this cubic curve where you have T going around the origin side. And the metric on the puncture disk is this. That's the hyperbolic metric upstairs, drop down to the puncture disk. So that means the length of a circle goes to 0. So the hyperbolic metric on the puncture disk, the circles around the origin have length going to 0 as they contract to the origin. The rays coming in will have length going to infinity, but only logarithmically. It's a complete metric. So let's go back to this mapping here. Take a sequence of points going to the origin, and this means analytically continue around the origin. So the length of the circle goes to 0. Now take the ratio of the periods and look at the distance between their images over here. The upper half plane is acted on transitively by SL2R. So this right-hand side, you can find something in SL2R so that it takes a fixed point to these 2 points. Use the invariance of the metric, and what you find is that this goes to the isotropic group, the point that leaves I invariant as n goes to infinity. So that means the absolute values of monodromy have norm 1. Right? It's a polynomial with integer coefficients. The roots have norm 1. The theorem of Kronecker said that they're roots of unity. That should be all fours with the thing out there. And this part of monodromy, I think I'll skip over this. For this one, you use estimates arising from what happens instead of going around the origin, what happens when you go in. So I think to conclude, I will say just a few words about what might lie ahead for Hodge theory. I'm not by any means going to try to predict what will lie ahead. Of course, there's the Hodge conjecture, which could be proved tomorrow, but most likely will not, and so on. So I'm not going to really try to predict. But I do want to mention one aspect of Hodge theory that, again, has an analysis component to it. Okay. So for this, I want to consider, again, an integral of an algebraic function. But here I want to put in an arithmetic condition. This should be, the polynomial should be a polynomial with rational coefficients. And you're going to integrate, say, from the origin to some small number nearby. So make this an actual, don't get into periods, you're just doing something local. Okay. What sort of number is this integral? So very informally stated, an old result of Siegel is assuming that this integral is not an algebraic function of the upper limit of integration. Siegel proves that it's a transcendental number. So a related conjecture due to Maxime and Zagier, and again informally stated, you can state it correctly maybe, Maxime, is that if you have a set of algebraic numbers, small, any algebraic relation defined over Q bar will arise from geometry. What does that mean? I'll explain it by illustrating. Go back to the cubic. Take a flex tangent. This is a really terrible flex tangent, but anyway. And that's a nearby line. Abel's theorem, as we saw, gives you this relation, which translates into this. So this is a linear relation among three transcendental numbers that arises from geometry. That's the sort of thing that the general conjecture, to me, reflects. So in general, there's the period conjecture of Grothendieck, again very informally related, would say that the algebraic relations among periods are due to the presence of some algebraic subvariety on the product. So periods tend to be transcendental numbers. They can have algebraic relations among them. Those, according to Maxime and Zagier and Grothendieck, should arise geometrically.
So what if I just say it's a linear relation?
So I mentioned this just as one aspect of Hodge theory that I think is very interesting and very deep, and looking at things in Hodge theory that might be done in the future, or certainly one area that certainly should be worked on because of its interest. The arithmetic aspects of Hodge theory is the one. Okay, thank you.
Any questions?
Yeah, so what is known about the last conjecture? The relations are very simple linear. Do you know the conjecture then? Or?
What did you say?
So, could you repeat your question? Maybe move forward.
What is known about the last conjecture? It's not only an algebraic, but a linear relation. Is the conjecture known there?
He says what is known about his last conjecture is not only an algebraic, but moreover a linear relation. Is this part of the conjecture?
Yeah, exactly.
I think your conjecture was general to be a polynomial relation.
Yeah, what if you know it's a very simple relation? Do you know that it comes from geometry?
Is it known for very simple relations, or is not known?
Yeah.
For very simple relations.
I mean, there are recent papers, for example, I was just looking at that seem to be state-of-the-art, talking about linear relations for abelian varieties. So then it gets into the linear independence of logs and stuff like that.
Maybe
Yeah.
give a comment actually. Right.
Louder, please. Yeah.
Okay, maybe just take micro. Okay. Yeah. Fantastic. Yeah. Yeah. In fact, a long time ago, Andrei Todorov told me that potential examples by Andrei Weil, have abelian variety, like four-dimensional this complex multiplication by imagining quadratic field, and then there are extra classes in middle homology for which you don't know representatives. And these days I more and more believe that maybe it will be a counterexample to all conjectures. And about 10 years ago I developed even a strategy to disprove Hodge conjectures using make tropical limit of these things. And for tropical limit it's a very beautiful story. It's much easier to disprove Hodge conjecture in tropical limit than prove one. So one can solve a huge system of linear equations and countable system of linear equations, and you can write explicitly.
Was there recently a paper about this?
Zharkov wrote
But he, if I remember looking at it, he tried but didn't quite get it. Is that right? Counterexample or?
No. The problem is even to write system of equations. Yeah, it's a bit very difficult, but in principle it should be kind of something amenable to the computer search. And
okay.
Yeah.
Sorry, so you think it would also disprove this?
Everything.
Everything.
Yeah, so there's a fair chance and kind of 50-50 believe that it's yeah, and also there was another development.
And that would be consistent with the sort of arithmetic aspect of Hodge theory, really.
Yes, it's also a Deline's theory of absolute Hodge cycles.
Right.
It's still okay, yeah, but.
But isn't the Deline result, that's to me very positive evidence.
Yeah.
So also not just the result, but the proof. You know, the argument is so beautiful that, okay, it doesn't prove what you want, but it almost does.
Yeah. And also there was, you see that all these questions use integration by parts with algebraic functions to prove identity between integrals, but there is additional tools to prove identity between integrals through non-commutative integrations of theory of code, which also produce some numbers.
Okay.
Integration replaced by traces of some algebras and some cycles of Fred-Gordon models into pure linear algebra, and it produce periods, but also some other numbers. He gave a talk recently on some conferences. That there are some other numbers coming from non-commutative algebras, but they form matrices of infinite rank. Yeah, so in principle they could give a way to prove that even in algebraic geometry one number is equal to another going through some non-commutative.
Okay. Thank you.
Any additional questions? Well, if not, let's thank Philip again.
Okay.
And we'll be back in 15 minutes, right?
No.
No, in 30 minutes.
Now there is a coffee break.
There is a
so
coffee
I would
break
like to
now.
Coffee break.
To invite you for a coffee
Tu sais, on va soumettre diverses synergies. Je vais conseiller oui, mais mes collègues allemands. Chacun fait ce qu'il veut. Il n'y a pas que je trouvais ça absurde. You are the chairman, or you are the chairman? No. I am introducing you. No, still 1 minute. Now. Oui. We're already there. Good start. So it is a pleasure to introduce Professor Jean-Pierre Bourguignon from CNRS and IHES. He'll be speaking today about revisiting scalar curvature. Professor?
Thank you very much for the introduction and the invitation. It's a great pleasure to be here. So I'm very pleased to be able to participate in person in this inaugural conference of this new research center. It's always a very important moment to start something new. And as you all know, it has been delayed by the pandemic for 2 years. Actually, it follows several meetings, and one which took place in 2015 that some of you attended, and which I was also there. And it was a very interesting meeting to show the strengths of Bulgarian mathematics in Bulgaria, but also outside Bulgaria. It was interesting. And so I'm very pleased that things could finally develop. And in particular, that it was really creative and active. And so it's very good. So this lecture is dedicated to some recent and not so recent developments about the scalar curvature, the Riemannian manifolds, the Riemannian metrics on manifolds. And a priori it looks like not so exciting because the scalar curvature is the weakest curvature invariant you can think of. So the first feeling you have is that there is not much you can say. It's so weak that you should not be able to say much. But it's quite remarkable that the subject has remained very, very active over the years. And there are still a number of problems which are not solved, and still quite a number of people working on them. And among the recent contribution, I think I need to call your attention to, there are two major ones. There is one which is a long document by Misha Gromov, more than 350 pages, which corresponds to 4 lectures that he gave at IHS in 2019. And well, if you're used to reading Misha, it means probably, I don't know, 150 theorems in 350 pages. So some food for thought. And you can also watch the lectures because they are definitely available on the IHS platform. But also a recent update on some sides of the question of the positive scalar curvature by Stefan Stolz, who has been one of the people who really contributed very significantly to the topic. It just has been, I think, completed in May this year, or April or May this year, which is also quite comprehensive. So it just shows that there is still a lot going on and new ideas, and my conclusion will be taking from Misha Gromov some new ideas that he will suggest that people should be looking into. So here is a summary of the lecture. Well, very general considerations of the scalar curvature, because maybe not all of you are familiar with the Riemannian geometry. The very special case, for reasons I will explain, dedicated to the issue of really describing manifolds which admit positive scalar curvature metrics. Then come back to the scalar curvature in the Keylerian setting, because there is, of course, in the Keylerian setting something specific to be said. Then an approach of some issues which appeared both in the real case and the Keylerian case, that one can look at some, I would say, abstractions or identities. One can look at them from a different point of view, and definitely for me at some point it was something which was very motivating. And then I will come to my concluding remarks. Okay, so this is the summary of the lecture. Let's start with the general considerations. So of course, as you know, the very important turning point in geometry was the, of course, the essay by Gauss, published in 1827, which is Disquisitiones et superficies curvas, which, as you know, I mean, the Gauss had in his door for probably 30 to 40 years before he published it, because he was unhappy not to have a very explicit formula, and he had all arguments to develop the concept, which is very important, which is the definition of the Gaussian curvature for surfaces. But then finally he had the formula he was happy with, and therefore he could publish. But of course, this was really the two-dimensional situation, which was already a very, very major point. I mean, the key point being that the notion of curvature that Gauss has introduced is intrinsic. It doesn't depend on the embedding. It's purely induced by the metric induced on the surface, hypersurface in R3. And then, of course, there is the lecture by Riemann, assumptions on which geometry is based, and which really generalizes widely the concept of geometry in an n-dimensional context, with in particular really the key point is that in this document, which was published after Riemann's death, actually there is only one formula, which is a formula which introduces the Riemann curvature tensor as an abstraction to Euclidean geometry. So the vanishing of the Riemann curvature tensor means that the metric, the Riemannian metric which has been introduced, actually you can choose coordinates to make it really Euclidean. And of course that's a very important object. And you see that it's very remarkable that the notion of Ricci curvature, which of course anytime you teach Riemannian in the geometry today, you introduce Ricci curvature at the same time as you introduce a Riemann curvature tensor, was introduced only in 1904, 50 years later, by Gregorio Ricci Corbastro. And it's very interesting that his motivation then was to actually mimic what happens for hypersurfaces, and in particular look at, because the Ricci curvature is also a symmetric tensor, in presence of a Riemannian metric, you can diagonalize the Ricci curvature, and therefore you introduce specific eigendirections for the Ricci at each point. And to my knowledge, I don't know any result in geometry which follows from this. So the initial motivation of Ricci was actually proved not to be relevant. Of course, the concept of Ricci curvature became absolutely central in general relativity, as you know. So it's very interesting to see that at some moment you could introduce something and have a vision how it can be useful, but in the end, the vision is not correct, but the concept is absolutely fundamental. And of course, the scalar curvature is just a trace of the Ricci curvature, and therefore, I just wrote for you in the normal coordinates, that is, coordinates which are geodesic at a point, the formula for the scalar curvature, which in particular shows the general formula, if you take general coordinates, will show not only this term, but also quadratic terms in the first derivatives. But if you are in the normal coordinates, as we call them, geodesic coordinates at a point, then it's just a linear expression of the second derivatives of the metric. So of course the upper Gij are just the inverse matrices of the Gij. Anyway, so this is the object, the scalar curvature. And actually, if you look at Misha Gorbachev in his series of lectures recalls something which is very well known, that the map, which to a metric associates its scalar curvature, is characterized by two properties which are very obvious. First of all, the equivariance vis-à-vis the actions of the group of diffeomorphisms on metrics and on functions. And of course, the fact which I just showed, that was my last line of the previous slide, that it depends linearly on the second derivative of the metric. And he also gives another characterization which actually is not so well known, which are, first of all, the additivity under products. So if you give yourself two manifolds with two metrics, and you look on the product manifolds to the sum of the two metrics, then the scalar curvatures add up. The quadratic scaling, which was by construction, because you remember that the scalar curvature was the trace of Ricci, and Ricci, as was recalled by Maxime, is invariant. And then when you take the trace, that is, you have to use the inverse of the metric, then you get this -2. And then the volume comparison is also a very important thing. That if you give yourself 2 points in two manifolds with two metrics, and then if you assume that the scalar curvature in the first manifold is less at the point P1 is less than the scalar curvature at the point P2 on the space, then if you look at the volumes of the epsilon balls around these points, in these two manifolds, then the volume is in the opposite direction. Of course, for epsilon small enough. So this is volume comparison. And Misha makes the comment that actually he doesn't know how one can use this, although it looks very important geometrically, but this is not so easy to. And of course, at some point you have to normalize the quantity, and of course, if you go back to the trivial example of the unit sphere in R3, its scalar curvature is 2, and of course the Euclidean space is flat, and the hyperbolic plane with constant sectional curvature -1 has scalar curvature -2. Well, I'm talking about two-dimensional objects. And the point I want to make is that there is one more reason for the scalar curvature to be important, which is not mentioned at all by Misha, so I'm going to stress that for me there is another reason why the scalar curvature is important, which I'm going to explain. And for this, I need to go back to understand a bit more in depth the curvature tensor. And of course, the most obvious property by the very definition of the curvature, it's a commutator of derivatives. So of course, when you look at the curvature on vectors x and y, and you exchange x and y, then you just get the opposite value, just almost by definition, by construction. But actually, you know, the covariant derivative, the Riemannian covariant derivative has a number of properties about symmetry, about, the metric being parallel with respect to the covariant derivative. And therefore, there are some other identities which come from this. So one is the fact that, which is connected to the fact that the covariant derivative is metric, that is, it preserves the metric. that if you exchange the last two arguments of the curvature, Z and U, you change the sign. That's the fact that that's an infinitesimal, it's anti-symmetry. And the other one, which has to do with the fact that the covariant derivative is symmetric, as we say, that has no torsion, then you get this Bianchi identity of the sum, alternating sum of the three vectors is 0. And therefore, because of the first identity C1, you don't want to introduce the metric all the time, so maybe you transfer your study of the curvature, which spontaneously is a tensor of type 3-1, 3 times covariant, 1 times contravariant. You make it completely 4 times covariant by just, having x, y, z, u be four vectors on which you evaluate the curvature. So I will be doing that. That is, I will be working with the curvature as a 4-0 tensor. And one consequence of the previous symmetry, which is a little exercise, is that if you exchange the pairs x, y, and zu, then you have a symmetry. So this is, of course, easier to formulate with the 4-0 version. And therefore, you can really look at tensors over Euclidean vector space, which satisfies all these axioms. As I mentioned, C3 is a consequence of the previous ones. Then we call them algebraic curvature tensors. And because of these properties, it's easy that you can view it as a subspace of the symmetric tensors on the wedge 2. It's a 4 tensor, so you expect it to be like this. And so it's an element in this vector space. But then the key point is that if you look at the space of symmetric tensors on two forms, then it's the space of curvature tensor, Re, direct sum with the fourth power of the dual space. And that's it. So it's an easy, small exercise to show that you have this decomposition. And actually this shows very obvious things. If you look at the small dimensions, for example, 2 dimensions, of course, lambda 2 is just 1-dimensional. So in curvature tensors in 2 dimensions, it's just a line. It's just a vector space of dimension 1, which corresponds to the Gaussian curvature, of course. When you are in dimension 2, of course, the lambda 2 of E star is just isomorphic to E star. So it's the same as the symmetric tensors. So therefore, the curvature tensors in dimension 3, you have only room for the Ricci curvature, nothing else. And it's only starting in dimension 4 that you have enough room for something else than the Ricci curvature, which I will show in a minute what it is. So my whole point here is that it's useful to break the curvature into pieces. So the first piece we already identified was the Ricci curvature. And the Ricci curvature, if you want to break it into pieces, you take the diagonal piece, which contains the scalar curvature, plus a trace-free part, which I call little z. So that's the decomposition of symmetric tensors into the diagonal part and the trace-free part. But then to express for 4 tensors, it's very useful to introduce what is called the Nomitsu-Kulkarni product. That is, you take 2 symmetric tensors h and k and make a 4 tensor out of them. So you multiply them in a sense, but you multiply them doing some kind of symmetrization. And so if you do this symmetrization, I will written here, then it's very important that what you obtain for any symmetric 2 tensors is actually a curvature tensor. And so that's interesting. And therefore now the decomposition of the Riemann curvature tensor is just given by this. There is some kind of, I would call diagonal part, which is just G, product G, with the scalar curvature in front, numerical coefficient. Then the trace-free part of Ricci, multiplied by G. And then what is left is the so-called Weil curvature tensor, which, as probably many of you know, is actually a part which is basically invariant under conformal changes, conformal change of the metric. So it's actually, I should say, covariance, not exactly invariant. Depends on the weight. So this is a decomposition into irreducible components under the action of the orthogonal group. So this is one reason why I said that there is one thing which is very important, that is the scalar curvature is the one-dimensional irreducible component in this decomposition. And actually this remark will be very important when you talk about spinors. So this is a little bit of algebra, which is actually very useful. And so now, what are the general questions about the scalar curvature? And the very basic question is, on a given manifold, which functions can be the scalar curvature of a Riemannian metric? And actually, I will be focusing on compact manifolds, but of course, you can ask the questions on, you don't have to look at this question for compact manifolds. You can look in particular for complete manifolds, complete metrics on manifolds, non-compact manifolds. One thing which is very well known is that if you're interested in surfaces, there is the famous Gauss-Bonnet theorem, which states that the integral of the scalar curvature against the volume element of the metric is actually a topological invariant. It's 2 pi the Euler characteristic, which of course introduces some restrictions, topological restrictions on what kind of metrics, what kind of scalar curvatures you can have for a metric on the surface. I'm again talking about compact surfaces. So on S2, because the Euler characteristic of the sphere is positive, a scalar curvature function must be positive somewhere, because the volume element, of course, is a positive measure, so you cannot have the integral being positive without the function being positive somewhere. On the torus, where the Euler characteristic is 0, then of course it means that unless the scalar curvature is identically 0, which of course can happen on torus, you have flat tori, actually it has to take both sides. And of course if you look at surfaces with a higher genera, then the scalar curvature has to be negative somewhere. So this is the case of surfaces. But then over the years, the question of manifolds admitting metrics with a positive scalar curvature has taken great importance, partly because there is a theorem which goes back to 1975, saying that if you start dimensions over 3, then all n-dimensional manifolds admit metrics with negative scalar curvature. And as you will see in a minute, the answer is not the same for positive scalar curvature. So this was really the starting point of these very general questions. And indeed, in the article, Castelnuovo referred to, well, break the n manifolds into 3 categories. The manifolds admitting a non-negative scalar curvature metric, which is positive at least at one point. So non-negative and positive at least at one point. And actually, for those manifolds, they established that actually any function can be realized at the scalar curvature of a metric. Then the second category is manifolds with a non-negative scalar curvature metric, but no metric with positive scalar curvature. And they show that then the function is the scalar curvature of the metric if and only if there is a point where it is negative or it identically vanishes. So this is the second category. And the last categories actually are indeed manifolds which do not admit a metric with non-negative scalar curvature. So this is the dichotomy. And in 1979, for n less than 7, Richen and Qingtung Yao using minimal surfaces, but then this was extended in 1980 by Gromov and Lawson using completely different technique, using spinoidal techniques. They proved that the n torus doesn't admit any metric with positive scalar curvature. So, which, I mean, was an open problem for quite some time, but that was settled. So I'm going to focus now on positive scalar curvature because, as I mentioned, it has been really looked into quite carefully. So the unexpected turn, in a sense, is resolved by André Lichnowitz. The initial key remark was made by Lichnowitz in 1963, in which he connected the existence of so-called harmonic spinors with the positivity of scalar curvature. So I'm going to explain this. So here is the story. Indeed, on a spin manifold endowed with a metric positive scalar curvature, non-vanishing harmonic spinors cannot exist. So, and of course I will explain all the terms of spin manifold, harmonic spinors, I will explain them later. And indeed, the reason why this really, why it comes that this is impossible is that the Atiyah-Singer index theorem implies that some spin manifolds must admit non-trivial harmonic spinors because of the index theorem. And typical example of 4K dimensional manifolds with a non-vanishing Ehrhoff genus. In a sense, the simplest example are K3 surfaces in dimension 4. And of course, this provides an obstruction to the existence of a metric positive scalar curvature for these manifolds. And this result has been refined by Nigel Hitchin in 1974, so sometime later, because, of course, everything I said so far was very much concentrated in 4K dimensional manifolds. But you can actually, if you sophisticate the Dirac operator, which so harmonic spinors mean a spinor which is annihilated by the Dirac operator. And if you use a more sophisticated Dirac operator and also invariants which are more general than Ehrhoff genus, typically KO invariants introduced by Sir Michael Atiyah, then the non-vanishing of these KO invariants obstructs also the existence of metrics with positive scalar curvature. And this is a way that Nigel proved that some exotic spheres in dimension which are, for which the remainder to division by 8 of their dimension is 1 or 2, actually have no metrics of positive scalar curvature. So it's kind of surprising that a sphere, of course exotic one, not the usual differential structure, have no metrics with positive scalar curvature. So this was the unexpected term. So I'm going to try to explain to you briefly all the terms which I've been using. So I do a quick introduction to spinor geometry. So spinors appeared in 1913 in a completely, in a sense, out of the blue. Elie Cartan was doing a classification of the representations of the orthogonal Lie algebras, and he found all the representations that people expected, plus another one, which was the spinor representation. And the key point, of course, I'm talking about Lie algebras. So that the space of spinors is actually acted upon by not SON, but the double cover of SON. So as soon as you are in dimension at least 3, this is the universal cover of SON. And so these objects, now the most efficient way of looking at them is to consider Clifford algebras. So if you take a vector space V with a metric, then the Clifford algebra is just a tensor algebra in which you force the relation x squared equal minus the norm squared of x times 1. So you divide by the double ideal generated by such elements. And actually the key property is that these Clifford algebras, if you look at them over the complex numbers, have a twofold periodicity. If the dimension is even, the Clifford algebra is simple. Therefore, it's an endomorphism algebra of some vector space. And if the dimension is odd, then the Clifford algebra is this direct sum of two endomorphism algebras. And so these two, the vector space sigma GV and sigma trivial GV are the spaces of complex spinors. And their dimension, it's easy to see because the Clifford algebra basically has a vector space or even a space of representation of the orthogonal group actually very similar to the exterior algebra. Therefore, the dimension is 2 to the power of the space. Therefore, if you look at it's easy to see that the dimension of the spinors is 2 to the m, can be either half the dimension or half the dimension minus 1. And of course, the key feature, which of course makes it very important, is that they are, as I mentioned, acted upon by the group spin n. And now the key point is that if you want to have this spin n action globally defined over a manifold, there is a topological restriction, which is that the second Stiefel-Widner class, which is a Z2 class, Z2 class 2 class, then must vanish. So if this is not true, then you cannot define globally spinor fields. And the very important point for later developments is that the usual constructions of Riemannian geometry, the covariant derivative, the curvature, carry over to spin manifolds. So you don't have to make further choices. It's as soon as you have chosen a spin structure, which is a globalization of the notion of spinner over a manifold, then you can really do the usual business. And then the very important operator, which was introduced by Dirac, is the operator which, when you apply it to a spinner field, which is a section of the bundle of spinners, is the most obvious thing you can define. You take a psi, you compute its covariant derivative in direction of EI, and you Clifford multiply by EI, which is the action of vectors on the spinners. And of course you sum over an orthogonal basis EI. So this is the Dirac operator. And now the very critical things, this operator has very interesting properties. It is a square root of the Laplace-Beltrami operator, and in the Riemannian setting, an elliptic operator. Its principal symbol is the Clifford multiplication. And actually it's exactly the reason why Dirac introduced it. Of course, he was not working with a Riemannian setting, but a Minkowskian setting, and he was looking for a square root of the D'Alembert, the wave operator, and of course, but everything goes in the same way. But very, very important for us that when you are in the even dimension, there is a further property of spinners, namely what we call the chirality, which is the fact that if you look at the action of the volume element with the proper power of I in front of them, then you can split the space of spinners into so-called positive spinners and negative spinners. And this is very important because I mentioned that the Dirac operator is self-adjoint, so therefore if you look for an index for a self-adjoint operator, of course you're going to get 0, which is not very interesting. And so, of course, the key point, because you, in the definition of Dirac, you have the multiplication by a vector, Clifford multiplication, so D exchanges chirality. So it maps positive spinor fields to negative spinor fields and vice versa. And therefore, for a spinor field psi, there is a very, very important identity which actually was first formulated by Schrödinger, but rediscovered by Lischnowitz apparently, which says that if you look at the square of Dirac, it is, as I mentioned, really the Laplace-Beltrami operator, but of course there is a curvature term, and then the comment I made about the fact that if you look at the decomposition of the curvature, so it's very clear that it will be a curvature term, but the only representation appearing in this curvature algebra, which can act on spinners, is only the diagonal part. It's only the scalar curvature. So, in a sense, completely abstractly, you can guess that the term which comes on top of the Laplace-Beltrami will be the scalar curvature. Of course, what is missing is the factor, which is 1/4, and of course the sign is not negligible, so you have to make sure the sign is the right one. But anyway, the fact that in the square of Dirac you have the scalar curvature is really built into this curvature algebra. And so that's what I just explained. And then, as I mentioned, harmonic spinners are just spinners which are annihilated by the Dirac operator. And then, of course, to prove that if you have positive scalar curvature and if you have a harmonic spinner, a non-vanishing harmonic spinner, then you have a contradiction. Is very, very simple because on the left-hand side you have 0 for harmonic spinner, if you take the square of Dirac, and on the right-hand side, if you take the right-hand side and take its scalar product against the spinner, you get d star d psi against psi. By integration by part, it's d psi squared, and the rest is scalar curvature times psi squared. And if scalar curvature is positive, you have a contradiction because you have 0 as a sum of 2 positive terms. Okay, so that's where we are, and therefore that's what justifies the result by Lischnowitz. Okay, so now concerning, in the sense, a spinor approach to the question of positive scalar curvature, as I will mention later, there are also other approaches, but the interplay between the spinorial nature of a manifold with the positive scalar curvature metric goes much further. Actually, in a paper in 1980, Gromov and Lawson proved a very important theorem. If you concentrate on simply connected manifolds of dimension at least 5, then the answer, the question of existence of a metric positive scalar curvature depends only on the spin Boltzmann class of the manifold. This is connected to what some type of surgery that you can do and preserving positive scalar curvature.
Sorry, I just realized that I don't know if you mean positive scalar curvature means somewhere positive or everywhere positive.
No, for me, I really mean, non-negative and positive, at least at the point.
At the point, yes.
Okay,
Just the point, yeah.
But then you know, if you know that, then you know actually you can make it really positive everywhere.
Oh, okay, thank you.
Yeah, I should have been more precise, thank you. And then in the same article, they also prove something quite surprising, if you think of it a little bit. Again, if you concentrate on simply connected manifolds, but the ones which are non-spin, dimension at least 5, then all admit metrics positive scalar curvature. Again, it's a surgery up. And why is it surprising? Because you know, I mentioned that being spin means that you have the vanishing of the second Stiefel-Widner class. So you would expect that something which, so non-spin means that this class is non-vanishing, and it's really difficult to imagine why the presence of such a weak object like the second Stiefel-Widner class would allow you to really make positive scalar curvature. Anyway, so that's the key point, of course, is how you can use surgery techniques. And actually, I mentioned the argument by Lischnowitz, extended by Hitchin, and then Stefan Stolz showed in 1992 that actually, if you look all the KO invariants, which I referred to, they form a complete set for simply connected manifolds in terms of obstructions coming from the Atiyah-Singer index theorem. And actually in dimension 4, you can, so again, I'm talking about the dimension 5 and above, but when you're in dimension 4, there's another invariant which provides an obstruction to the existence of metric positive scalar curvature, which is the Seiberg-Witten invariant, which, as you know, is an interesting twist using spinors of a system of equation mixing forms and spinors. So now, continuing for this non-simply connected, so this was for simply connected manifolds, but of course for non-simply connected manifolds, in another paper, Gromov and Lawson at the same time, slightly later, introduced, actually published in the Publication Mathématique de l'IHS, introduced original constructions of new obstruction to the existence of metric positive scalar curvature connected to the structure of the fundamental group. And so there were many refinements looking at the categories of fundamental groups more and more complicated. And in particular, the people who contributed a lot were Rosenberg and Stolz. And therefore, Stolz in particular in this comprehensive report, which I just mentioned as one of the recent contributions, describes where the problem stands, and again, the categories of groups, fundamental groups for which you now, as results, has continued to grow, but it's not yet completely finished. So this is very important. And again, in all these results, index theorems for twisted Dirac operators and metric surgeries play a key role. So it's a combination of topology and this kind of, index theorems. So I'm moving now to the scalar curvature in the Keynerian setting. So, well, just to be, not to be too tough on you, I just make a basics of Keynerian geometry. So I'm going to consider an n-dimensional complex manifold. So n is the complex dimension. We consider a triple, which is a Riemannian metric, an almost complex structure, which is integrable. I'm supposing the manifold is complex, and for which the G is Hermitian with respect to the almost complex structure. And then it's very natural and useful for two tangent vectors at a point to introduce a skew to form omega, which is defined by omega of xy is G of jxy. And automatically, because of the Hermitian character of G with respect to J, then this is omega is Q. And then the triple is said to be Keynerian in these two forms. exterior two forms is closed. And then, of course, if it is closed, by Durham cohomology, it determines a cohomology class. And this cohomology class, of course, is peculiar because it contains a non-degenerate two form. And of course, actually, M omega, if you think of M with this exterior two form, is just a symplectic manifold. And it corresponds, using J, to, well, what is specific is not only the non-degenerate two form, but it corresponds within the scalar, the almost complex structure to a positive definite metric. So this is what we call a Kähler class. And already in the original article of Kähler, right at the title is really some remarkable Hermitian metrics. That's the title of the article by Kähler. He considers the case where the class is trivial, which means that one can find a function u, which is a Kähler potential, so that the exterior two form is I t d bar of this function. And so when the class is non-trivial, one can always consider deformations of the Kähler metric, omega, by considering Kähler metrics trivial omega, which is just omega plus I t d bar phi. But of course, phi has to be small enough that omega trivial remains positive definite, because of course, you can destroy the positivity by adding a term like this one. So this is really the basics of Kählerian geometry. But of course, we have to go to the curvature, and then special properties of the Ricci curvature in the Kählerian setting is very natural. Actually, you do with Ricci what we did with the metric. That is, we consider the two form, rho omega, evaluated of xy to be Ricci of jxy. And the good news, which is connected to the symmetries of Ricci, is that rho omega is actually a skew form. So, and if you look in complex coordinates z alpha, the metric has a local expression. G is g alpha beta bar dz alpha dz bar beta. And Erich Kähler already had the key formula that local expression of the Ricci form is minus I t d bar logarithm of determinant of g alpha beta bar. So in modern terms, it says that rho omega, the Ricci form, is the curvature form of the canonical line bundle of complex forms over M. And therefore it is, so for the moment I said algebraically it was closed, it was skew, but now we have also the fact that it is closed. And of course, and even more than that, it's exactly 2 pi times the first Chern class of M, which of course is a very fundamental fact in Kählerian geometry. And then of course the Kähler geometry has been dominated by the question of prescribing the Ricci curvature. But you know that you have this constraint, that the cohomology class of the Ricci curvature has to be 2 pi C1. And as a result, in the Kählerian setting, the scalar curvature can also be expressed as the scalar curvature times the volume element, which is the Kähler form to the maximum power, complex power, complex dimension, is the Ricci curvature wedge with the omega to the n minus 1, which is another way of taking the trace, which is just by multiplying by omega to the n minus 1. So in the Kählerian setting, the scalar curvature appears in this way, which you see what is interesting. I'm taking the wedge of forms which are closed, so there is a cohomological interpretation for this. And so the search for Kähler-Einstein metrics, that is metrics for which the Ricci form is a multiple Kähler form, has been a very important driver of the research in Kählerian geometry for a number of years. And it has been actually accompanied by the more general study of constant scalar curvature Kählerian metrics. And the first necessary condition is that the first Chern class, if you want the Ricci form to be a multiple of the Kähler form, then you know that the class determined by Ricci is up to 2 pi in the first Chern class. So of course the first necessary condition to find the Kähler-Einstein metric is of course that the first Chern class must either vanish or be definite. definite positive or definite negative, because it has to be a multiple of the Keller form. So for C1 negative, existence of Keller-Einstein metrics has been obtained by Thierry and Xingtung Yao. The case C1 0, meaning that you take the Ricci curvature to be identically zero, which is something that Maxime referred to this morning, follows from the solution of the Calabi conjecture by Yao, since it just means that you have to find a Keller form for which a Ricci identically is zero. But then the case C1 positive has been, which corresponds to the so-called Fano manifolds, has been much more subtle, because there are a number of instructions to finding a solution to this equation connected to the holomorphic geometry of M. And this has been really. So the first obstruction, which was known for quite some time, is due to Yozo Matsushima, because he showed that if you have a Keller-Einstein metric, actually the group of holomorphic transformations of M has to be reductive, because actually it should be a complexification of the group of isometries, and therefore it has to be, it forces it to be reductive. And actually Nishnowitz showed that this result doesn't depend on having Keller-Einstein, but having constant scalar curvature is also the same case. So here is an obstruction to Keller metric with constant scalar curvature is the reductivity of the group of holomorphic transformations. So a further obstruction, which actually is inspired, and Futaki is very explicit about that, by considerations related to scalar curvature in the Riemannian setting, has been introduced by Akito Futaki. So if you are looking for Keller-Einstein metrics, you need to start with, of course, Keller class, which is a multiple of the first John class. And therefore, because you know Ricci, the Ricci form is also in the same class. So if you take the difference between the Ricci form and the Keller form, then it must be an exact form. So there is a certain function, phi omega, which measure, in a sense, the Ricci deviation in this setting. And then Futaki had the idea of introducing a function on the Lie algebra of holomorphic vector fields, which is the following one. So that's capital phi sub omega applied to x, which is just a holomorphic vector field, is the integral over m of the Lie derivative of the function little phi omega, that is the one which is measures the deviation from Ricci to Keller, to the Keller form, integrated against the volume element. And then the key point is that this quantity, which a priori depends on the choice of omega in the Keller class, actually does not depend on the choice of omega in the 2 pi C1M cohomology class. So this is what one calls the Futaki character on the Lie algebra. And actually you can also define it for non-Fano manifolds, so you don't really need C1 to be positive. And in this case, what you do, instead of comparing rho omega to omega, because in the context of Keller-Einstein they have to be cohomologous, but you compare it with the harmonic representative for the Keller metric omega of C1. And again, you end up with having the Futaki invariant, or character, as you want to call it, as an obstruction. Its vanishing is a necessary condition for the existence of a constant scalar curvature metric on the manifold. So now I'm going to come back to these ideas of integral invariance. So let me come back to what inspired Futaki, actually, which is in their 1974 seminal paper, Kasdan and Warner considered not just the question of describing metrics with positive scalar curvature, but the very, very specific question of describing the scalar curvature of functions of metrics which are pointwise conformal to the standard metric on S2. So you're not just looking at any metric, but the ones which are exactly pointwise conformal to the standard metric. So that's what one calls a Nienberg problem. And they discovered that besides the constraint coming from the Gauss-Bonnet formula, the scalar curvature functions must satisfy another constraint, namely that if you take a first spherical harmonic on the sphere, then the integral of the Lie derivative of the scalar curvature in the direction of the first spherical harmonics integrated against the volume should be 0. So of course, this means, for example, that any function which depends in a monotone way on the distance to a point, because you just take the spherical harmonics which correspond to this point, is forbidden, cannot be a scalar curvature of a metric conformal to the standard metric. And of course, in a sense, as I said, their proof uses the fact that the first spherical harmonics on the sphere are just restriction to S2 of the linear functions in R3. And actually you can, so they looked at this for 2 dimensions, but you can look at this problem, again, conformal metrics which are pointwise conformal to the standard metric in any dimension, and you can pose the Nuremberg problem in any dimension. So I want to revisit this identity and this question and show that it is actually of a rather universal nature and not just connected to first spherical harmonics. And actually the proof is elementary. So the key point is that we will have to work with the space of geometric objects, which are called O here. And of course, we will look at, on this space of geometric objects, we will look at some closed differential one-forms alpha, which are invariant under the group G, which operates on this space of geometric objects. Then if you take an element X in the Lie algebra of G, then, of course, because the form is invariant, its Lie derivative in direction of any element in the Lie algebra of the one form is 0. But then you use the Cartan identity for the Lie derivative, which says that the Lie derivative in direction of x is xt plus dix. And therefore, since you assume you know that alpha is closed, the only thing you're left with, if you have Lx alpha equals 0, is that the differential of the function Ix alpha is 0, which means Ix alpha is a constant on your space. So this is the context. And my claim is that both the Kasdan-Warner identity and the Futaki invariant are actually obtained if you choose appropriately the group, the space of geometric objects, and the form. And so for the Nuremberg problem, which was the one considered by Kasdan-Warner, we fix a conformal class gamma of metrics on M, and we take G to be the group of conformal transformations. And of course, for an element in the group and a metric in the conformal class, the action is just the usual pullback by the transformation. And actually, it will be convenient, it's not necessary at all, but just to discuss it simply, to identify the conformal class with the volume elements. So if you're in n dimension, it means that for a metric which you would write as G equals e to the 2f G naught, with some kind of reference metric, then the volume element will be e to the nf, the volume element of the reference metric, just conveniently. Therefore, the tangent space to the space gamma is just at G, which means at Vg, is therefore just a space of differential n-forms. Let's assume M is oriented for simplicity. Okay, so that's a tangent space. And therefore, if you take a vector field in the Lie algebra of the group of conformal transformation, the vector field x bar at V, we are a point in gamma, is just x bar at V is just the Lie derivative in direction of x of V, just because the action is just action by composition. And therefore, of course, I was looking at the tangent space at gamma, but I should look also at the cotangent space, because I want to talk about the differential one form. So what is a differential one form? Well, the cotangent space is just a space of functions, because the tangent space is placed the volume element, so the cotangent space is the space of functions. And therefore, a differential one form, so a gamma, associated to a metric in the conformal class, is just a function on it. And for the Nuremberg problem, the differential one form on gamma we have to consider is just a form, sigma, which to a volume element associates the scalar curvature. Okay, so, and therefore then the differential form sigma on my space, on my gamma, on my space of conformal class, is closed. And the reason is that if you look at the formula for checking whether it's closed, just a very direct formula, is just a consequence of the fact that if you look at the variation of the scalar curvature in the direction of a function f, then you get the operator, which is listed here, 2 times n minus 1 Laplacian of f minus 2 times scalar curvature times f. It's a self-adjoint operator. And just the fact that it is self-adjoint implies that the sigma is a closed form on gamma. And on top of that, sigma is also invariant by the group of conformal transformation because that's just the naturality of the scalar curvature. And therefore, we obtain that for any conformal vector field x, the integral over m of the Lie derivative of the scalar curvature against the volume element is a constant. But actually, this constant is actually 0. Why is it 0? Well, either the group of conformal transformation is compact, and therefore you take as a metric, the metric, you just average the metric using the group, and therefore it's constant. You get automatically that the derivative is 0 because the SG is a constant, or it is the group of conformal transformation on the sphere, but that's the only case in which the group of conformal transformation is non-compact, and then you just take the standard metric. So, in the sense, you get the Castanweiler identity, in the sense, for free, without doing much computation. And of course, I want to say that, of course, this approach leads you naturally to consider other forms than just the scalar curvature. And first, the key point about this one form sigma on the space, on the conformal class, when the dimension is at least 3, actually this form is actually exact. That is, it is the differential of a function. And this function is just the total scalar curvature. Because what is specific to dimension 2 is that it is closed without being exact, but in a higher dimension, it's actually exact. And therefore, it's natural to look at other functionals. So, for example, if you take not the scalar curvature, but now the case power of the scalar curvature, then, for which, of course, the sigma 1 will be just the sigma I mentioned before, then you have the differential of this function, which is this, and therefore you see in particular that if the dimension is 4k, then the last term in the formula disappears, and then you get another identity, which is valid in 4k dimension, which is not only is the Lie derivative in direction of x, a conformal vector field of the scalar curvature, integrated against the volume element is 0, but also the same for its Laplacian, which, but you can, of course, that was just an example I gave. And then another family of closed differential one forms on gamma is given by the characteristic invariance on M. So it's well known that the Euler characteristic of a 2k dimensional manifold, I mentioned the case of surfaces for k equal 1, but for any even dimension, the Euler characteristic is the integral of a certain polynomial in the curvature of degree k. And independently of the dimension of M, on gamma, the differential one form, chi sub 2k, which is given by this specific polynomial, is closed and invariant, and therefore you obtain another identity, which is that for any conformal vector field, the Lie derivative of this polynomial invariant is equal to 0. So, which is interesting. And then now I want to finish by just telling you about the Futaki invariant. So in the Canadian setting, you have your complex manifold. Then the group will, of course, be the group of holomorphic transformations. And the space of geometric objects would be a Keller class, which I will use the letter K for that, which means which I want to view as the open subset of the space of function psi, so that the Keller metric omega 0 being taken as origin, then you have omega 0 plus I d bar psi is a Keller form. So my space of geometric objects is a space of functions. And then, of course, you need to find invariant and closed differential one-forms on K. And in our description, what is a tangent vector to K is just a function on M. And the cotangent vector is a differential form, 2M form, top form. And if to a Keller form omega, one associates the differential 2M form rho omega, the Ricci form, wedge with omega to the n-1, then actually one gets the Futaki invariant. And this differential one form on K is invariant because holomorphic transformations commute with I d bar. And you can note also that the two form of type 1 is the Lie derivative of omega in direction of the holomorphic vector field X at the point psi in the Keller potential belongs to the image of I d bar. And therefore that's sure that actually the Lie derivative of omega 0 plus I d bar psi is actually I d bar of some function psi x. And therefore the value of the vector field x bar acting on my space K is just this psi x. And then the coincidence with the Futaki identity follows from splitting rho omega into its harmonic part and its exact part, which is exactly I d bar of phi omega, which is the phi omega of Futaki. So you recover the Futaki invariant in general form. But of course it leads you to suggest other closed forms than just this one. Okay, so now I'm moving to my concluding remarks. So actually I've been following two quite different paths. One is connected to the Nuremberg program, which of course relies on subtle analytic estimate. That is the case where you look at just the conformal class pointwise metrics which are pointwise conformal to the standard metric on the sphere. And then the other paths were the more topological one, dealing with metrics with quantity scalar curvature. But there are, of course, a number of issues I didn't cover. All results mention only compact manifolds, when many recent developments deal with complete metrics on non-compact manifolds. Also, the importance taken in recent years by metric spaces with just some geodesic regularity is also perceptible in relation with scalar curvature. And one has to make sense of what is the scalar curvature for a space which is very irregular. For example, a metric space with just some geodesic regularity, and bounds on the scalar curvature, because giving value is not easy, but getting bounds is easier. And this is one of the issues that Gromov discusses at length in his 4 lectures. And also I favor the approach involving spinners or spinor fields over more analytical approaches using global analysis or geometric measure theory. That's part of my campaign to get more attention given to spinoidal geometry. But for the Nuremberg problem, which is in a sense the object of describing the set of so-called admissible functions on S2, that is metrics which would be scalar curvatures of metrics conformal to the standard metric. Actually, it has been a very interesting, it has stimulated a lot of delicate estimates. One is a beautiful result by Jürgen Moser, the so-called improvement of the Trödinger inequality, who proved that a key constant could be improved in the Trödinger inequality provided you impose to the function to be invariant until the antipodal map, which means they descend on RP2. And so, again, to review things on the Nuremberg problem, so as I said, the objective is to describe for which functions k, the equation Laplacian u plus k eu equals 1 as a solution, since this equation tells that the metric g equals e to the 2u g1 as curvature k, and of course the Laplacian is taken for the standard metric. And the identity found by Kasdan and Warner allowed to identify some explicit forbidden functions, as I mentioned. But actually, with Jean-Pierre Hézin, we proved that you can find other forbidden functions, but you cannot restrict to the formulation of Kasdan and Warner, speaking only of first spherical harmonics. You have to use the full conformal group. And we also showed that the set of admissible functions has a rather intricate structure with really its closure can be described, but its image is rather difficult to describe. And my final slide is borrowed from Gromov. Gromov has a section in his set of lectures which is, he says, scalar curvature, who are you? Which interesting question too. So I borrow from Gromov the title of this section, but here are some points that he makes which I think are absolutely valid. What are most general geometric objects that display features similar to these manifold, positive and more generally bounded from below scalar curvatures? Okay. Second question that Misha is posing, is there a direct link between Dirac operators and minimal varieties? Because I said for some results you have proofs using Dirac and you have proofs using minimal varieties. Or is there joint appearance in the ambience of scalar curvature purely accidental? Which I think is a very interesting question from the geometric point of view. And actually concerning this is more specific and asks, is there a partial differential equation or something more general, because he wants to do it also for singular spaces, the solutions of which would mediate between twisted harmonic spinors and minimal hypersurfaces. So that's some kind of a specification of the previous question. And as I suggested, Misha is especially interested in the coarse geometry of spaces with scalar curvatures bounded from below, where an appropriate meaning can be given to such an expression. I thank you for your attention and long and successful life to the ICMS-Sofia. Thank you.
Quick question or comment?
Try to have a small question. This closed forms which you construct on various infinite-dimensional spaces, are they related to some zeta-regularized determinants? And because it's at least for track invariance, one can.
That's true. I've not looked into that, yeah. But that's a good question, because of course you, in particular for in the Canadian setting, you would like to invent to consider some closed form which are really connected to more sophisticated things than just Ricci form, and so maybe this could lead to some other approach. By the way, in the Nierenberg problem, another invariant which is closed form you can look at is the first eigenvalue of the Laplacian. And what you get as gradient, as a differential one form connected to this function, is actually the square of the eigenfunction. And so you get an identity similar to the Kaslan-Warner identity, which says that the Lie derivative in the direction of a conformal field of the square of the eigenvalue for any eigenvalue gives also rise to some kind of identity. But I think you're correct in saying that we should look for other types of functional, in the sense, which you interpret as differential one forms.
So this is a very much a naive question. So I always feel it is very strange that what is Dirac operator, this Weizenberg formula has a very simple form with scalar curvature, but you consider usual differential form and usual T. Then this Weizenberg form has more complicated curvature term. Are there any intuitive reasons that this is so simple in the case of Dirac?
I don't know. I mean, in a sense, the reason why I focused my attention, actually when Nishnowitz mentioned this, it was a very big surprise, because everybody believed, in particular in the 1960s, that the scalar curvature is such a weak invariant that it's not going to be obstructed. And so it was really a surprise, because, and so the question is whether you could have some more other operators than Dirac, which is the simplest one you can think of, in particular looking at the spinor fields. But maybe if you look at the spinors of higher spin, which physicists would automatically try to do, because why should you concentrate only on spin 1/2 object, whether you can also have some other types of constraints which appear using more sophisticated, not just for Dirac, or other operators. But I don't think anybody has been looking at that. Mathematicians really constrain the attention to spinors to 1/2 spinors. When, physicists, of course, don't do that. You look at spinors for higher spins, and, because they are particles which have higher spins, so they have to look at them. But mathematicians tend to focus purely, which of course is already extremely interesting. But,
well, let's thank Professor Virginia again. I'm going to start 5 minutes late at 10 to. Thank you very much. 2 more minutes. 2 more minutes.
2 more minutes.
I gave
Okay.
them,
Well,
I gave them 5 minutes.
Such precision.
Maxime is only arriving. Well, let's start. It is a pleasure to introduce Professor Tony Panter from the University of Pennsylvania, who will be speaking about the moduli of local systems and flat connections on a smooth array. Tony?
Thank you. It's a great pleasure to be here and to kick off finally officially the new institute, even though it has been functioning for a few years now. Okay, it's the last talk of the day. Everybody's tired, and by coincidence, it's probably going to be the most technical talk of the day. So it's great because you're tired, you won't spot any of the mistakes. It's not on. It looks on. Oh, okay. All right, so I'm going to talk about moduli of local systems and flat connections on smooth algebraic varieties. And it's a joint work, in fact, a sequence of joint works with Bertrand Toen. And what we set up to do was to study the geometry of those moduli, the moduli of bundles with flat connections or local coefficient systems on a smooth, non-compact, non-proper variety over some field of characteristic 0. And we wanted to do it algebraically. So, I mean, of course, you can think about the complex numbers, but there are some subtleties that appear in the general field case, which I'll mention. And the goal was to really understand how standard results about curves, non-compact curves, generalize to higher dimensions. So how can we construct Poisson structures on such moduli? And how can we understand their symplectic leaves? So let me recall the classical story, which in some form you probably have seen, and I'm going to fudge it up a little bit and make it a little bit more advanced so that we can generalize to higher dimensions. But so here is a classical statement. If you have a compact-oriented topological surface, compact for now, and a complex reductive group, then many people in various ways have understood the symplectic geometry of the moduli space of representations of the fundamental group. So I listed some of the names, and there are many others. But so if you look at the moduli of representations of the fundamental group of the surface with values in the complex reductive group, it actually has, okay, I said compact, but I made a statement in general. So for any surface, compact or non-compact, but algebraic, so if you need to take compact surface minus finitely many points, then the representations of the fundamental group are a complex algebraic variety, which carries naturally an algebraic Poisson structure. And the symplectic leaves of that algebraic Poisson structure are given by fixing conjugacy classes of the monodromy at infinity. So if you look at the points at infinity that would compactify the surface, look at the loops around them and fix the conjugacy classes of the images of those loops for the representation, then you get a symplectic space. And so the way I've stated this statement, it's not quite correct because these spaces tend to be singular. So it's really a correct statement for the smooth parts of those spaces. But I'm going to extend it slightly in a moment to make it correct everywhere. And what you really want to do is you want to extend this statement so that it makes sense for all representations, not only the representations which happen to be smooth points of the moduli space. And you also want to extend them to a higher dimensional variety, not necessarily the surface. Okay, so I'm going to say the results and then I'm going to spend some time actually explaining. So fix a field of characteristic 0 and look at the d-dimensional smooth complex algebraic variety and a reductive algebraic group G. Then you can look at G-local systems on X.
You mean bundles with connections?
No, I mean, this is the Betti statement.
Complex variety.
Yeah, it's a complex variety. So it's a Betti statement. And I look at the moduli stack of G-local systems, and I really want to look at it in its derived version with some higher degree nilpotence, higher homological degree nilpotence in its function theory. And the claim is that the same statement as for surfaces holds. It has a natural Poisson structure, only this Poisson structure has some homological shifting by the dimension, and the shifting is 2 minus twice the dimension. So if the dimension was 1, there is no shifting, it's an actual Poisson structure, but in higher dimension there is some shifting. And this shifted Poisson structure also has many symplectic leaves, generalized symplectic leaves, because we're dealing with these derived stacks. Among those, again, you have the analog what we had for surfaces. These are G-local systems with fixed monodromy at infinity, conjugacy classes of monodromy.
Okay, sorry, Tony.
Yeah.
But I think this theory is not about complex manifolds, about smooth manifolds with a boundary.
No.
Or you consider oriented manifold with a boundary?
No. In fact, it's not even true for complex manifolds. I'm going to say there is an actual phenomenon that. I mean, yeah, okay. This one.
Yeah, this one. Yeah.
This one is true for oriented manifolds with boundary,
yeah.
But this statement is not.
But you consider real boundary at infinity?
Yeah.
Even this?
Yeah, this statement is not. And in fact, even in the complex case, there is a subtle condition that one needs to impose at infinity in order for the symplectic leaf, for the conjugacy classes to select the symplectic leaf, and I'm going to talk about it. But yeah, you're right, this one is correct for manifolds with boundary. But then there are analogous Deram statements, which I'll talk about in a moment, and of course those are over algebraic guys. Okay, so let me just make some comments. When the dimension is 1, the Poisson structure is the Goldman Poisson structure of the moduli representations. Part 2 is really subtle. You need to understand how to fix the local monodromies in the derived setting. And there are subtle issues. One is that you cannot see the condition on the local monodromies on the truncated moduli stack. If you ignore the higher degree homological nilpotence, then there is no natural condition that will give you a symplectic leaf. And if you don't ignore them, there is a condition. And it's actually a condition that was discovered, coincidentally again by Victor Ginsburg, many years ago in representation theory, which we call strictness, and I'm going to explain how that condition appears here. It's not the same condition that Maxime was mentioning about the cyclic labial algebras, but it's very similar. Okay, and let me say the DRAM statement. The DRAM statement, we start with d-dimensional smooth algebraic variety over the field K. And now we look at the derived moduli stack for bundles with flat connections. It has again a natural 2 minus 2 D shifted Poisson structure. But now you want to look at symplectic leaves. So you want to really be able to pose conditions at the boundary. And this turns out in the algebraic setting to be a very delicate problem. So there is a well-defined derived stack of moduli stack of flat bundles with flat connections on the formal boundary of X.
And so your bundles now have regular singularities?
No, arbitrary singularities. Yeah, not necessarily regular. But there is a notion of a formal boundary. And in fact, you know, the way I'll talk about the actual mechanics of this, but you really need this point of view of non-commutative geometry that Maxime introduced in order to actually talk about that flat bundles with flat connections on the formal boundary properly. And you can realize the shifted Poisson structure as you expect it's realized as a symplectic groupoid, as a Lagrangian structure on a map from the vector bundles with flat connections on X to the vector bundles with flat connections on the formal boundary. So this thing will be symplectic, and this thing will be a Lagrangian in that symplectic thing. And the fiber of that map is a flat bundles with the fixed restrictions to the formal boundary. This turns out to be a derived algebraic space, which is locally finite presentations almost. So there is some one of the finite type conditions is not quite satisfied. You need some Fredholm property in order for it to be satisfied, but it doesn't affect the existence of Poisson structures. So it's not quite algebraic, but it's almost algebraic. Okay, so these are the results. And again, this formal boundary should encode the punctured formal neighborhood of the boundary divisor in a good compactification, adding something with normal crossings to compactify. And you can describe either rigid analytic or non-commutative models for the formal boundary in terms of shift theory. So this was done in a sequence of papers in the past maybe 7 years, starting with the paper of Bembasat and Tyomkin, and then Efimov, Ihenion, Porte, and Vezosi. They describe the coherent shifts on the formal boundary, and so you can think about this formal boundary as this formal punctured neighborhood at infinity as a non-commutative algebraic variety, and then you can study the moduli of those coherent shifts. Unfortunately, that doesn't quite work for D modules, so you need to do something in order to get the D modules on the formal boundary. So the rigid analytic approach kind of works, but it's hard to work with, so we do it algebraically. So I'll say some words about that. Okay. So the bulk of the work for this DRAM statement goes in constructing the derived stack of perfect complexes with flat connections on this formal punctured neighborhood at infinity. And already for the case of A1, already for the case of the affine line with the boundary being 2 points that compactify to P1, this is a very difficult problem, but luckily it was actually studied in depth in Sam Raskin's thesis, because it's needed for understanding the RAN spaces of loop groups in dimension 1. And so that gave us a lot of insights of what to do in higher dimensions. So we defined that category of complexes of flat bundles with flat complexes of bundles with flat connections on this formal boundary, and we can study moduli problems of such creatures. We defined the stacks, derived stacks of bundles of with flat connections, perfect complexes of bundles with flat connections on a variety and on the formal punctured neighborhood at infinity. They are not algebraic, but they're formally representable at field value points. And this is enough to define symplectic Lagrangian or Poisson structures. And then when you look at the fiber, as I said, is almost algebraic. And then again, the Lagrangian structure that you want to construct that will give you the Poisson structure is some incarnation of Lefschetz duality or Poincaré duality for compactly supported cohomologies relative to a derived test scheme.
Sorry, Tony.
Yeah.
No, I want to really specify. You really consider connections with possibly irregular singularity?
Possibly irregular singularity.
But I think it's kind of not really the same because you mix different effects, non-compact manifolds. And
no, so I didn't. If you were careful, you'll see that I didn't mention anything about the symplectic leaves, and that's because in order to do the symplectic leaves with the irregular singularities, you also need to fix Stokes data and the formal monodromy. And you still get this strictness condition on the formal monodromy, but I don't want to talk about the Stokes data.
Yeah, because but in general, I think it's one can really separate issues.
Yeah, you can separate the story. In fact, if you want to compare the Betti, so the Betti version, of course, only sees the regular. And if you want to compare the Betti with the de Rham, you need to restrict to regular singularities in infinity. But we actually haven't looked at the comparison problem. We only looked at the Betti question separately, the de Rham question separately, and we kind of somehow dealt with different issues in the two cases. Yeah, so there is no harm in restricting to regular connections with regular singularities, and already all the phenomena that one sees appear there. And if you want irregular singularities, then there are additional difficulties because of the Stokes data. And so there is a different story about constructing the Poisson structures on modulo F Stokes data, but it's not part of this story. So
because in general, I think it's, if you deal with irregular singularity, you should consider compactification of cotangent bundle with some kind of
exactly. Yeah. I mean, the part of the Stokes data, it involves this.
It's not
this
really about manifold.
Okay, so let me now talk about how this is done and what the ingredients of the story are. So I'm going to talk about modulo F local systems, and as Max mentioned, the Poisson structure is really about oriented manifolds. So start with a finite CW complex and an affine reductive group. So I want to look at the modulo Stark G local systems on X. So these are locally constant principal G bundles. This has a natural structure of a derived algebraic stack over the base field. So it has local symmetries, which are groups, and it also has some derived structure. The function theory has these nilpotents that sit in negative homological degrees. But if you ignore those, the underlying moduli stack depends only on the fundamental group of X. It doesn't depend on the actual CW complex. It depends only on the fundamental group of this CW complex, only on the first stage in the post-Darwin. And it is just the moduli stack of representations of the fundamental group into G. So you look at all homomorphisms. This RG is all homomorphisms from the fundamental group into G. So this is an affine algebraic variety because the fundamental group is finitely generated. So you can choose in fact, it's finitely presentable. So you can choose a presentation and get a subvariety, a closed subvariety in a product of several copies of G. And then you need to model by conjugation. That's why it's stack, because the portion by conjugation has stabilizers. So we have this character scheme. It is the one that represents the functor that sends commutative algebras to group homomorphisms and then quotient by G. So this truncated guy, the stack of local systems, it has a coarse moduli space, which is the affine GIT quotient of this character variety by G. And the K points are just conjugacy classes of representations that have the property that the Zariski closure of their monodrome is reductive. And these are isomorphism classes of locally constant bundles. I mean, semi-simplifications of locally constant bundles. In general, if you want the derived moduli stack, it actually depends on the full homotopy type. It depends on the higher cells. And I have some slides explaining that, but I'm going to skip that. Just the message is that it depends on the higher cells. It's not just something that depends on the fundamental group. And that's why these conditions at infinity become subtler. Okay, now I just want to recall some yoga of these shifted symplectic structures. So it says that if we have an algebraic stack which is locally affine representation, and it's maybe derived, has derived function theory, then there is a complex of closed two forms on that stack. And when this algebraic stack is, say, corresponds, it's an affine, it corresponds to a commutative differential graded algebra, then this complex of closed two forms is just the totalization of the pit step of the Hodge filtration on the cotangent complex of that commutative differential graded algebra. And a cocycle in that complex, say a degree n cocycle, is what we call a closed n-shifted two form. And an n-shifted two form is called symplectic if it's closed, if it's one of these cocycles, and if it has the property that the contraction with that form from the tangent to the cotangent complex induces an element, this should be an n-shifted cotangent complex. It goes from the tangent complex to the n-shifted cotangent complex because it's a degree n cocycle. This guy is a quasi-isomorphism. It's a quasi-isomorphism from the tangent complex to the n-shifted cotangent complex. There is a typo here which is shift by n. Is missing. Okay. And there is a notion of a Lagrangian structure between such creatures. So if you have a map of derived algebraic stacks, an n-1 shifted isotropic structure on such a map is a pair where you have omega and h. Omega is an n-shifted symplectic structure on the target, and h is a homotopy between the pullback of that n-shifted symplectic structure and 0 inside the complex of closed two forms on the source. And an isotropic structure is Lagrangian if it satisfies the usual non-degeneracy condition. It says that the contraction with that homotopy by that homotopy between the relative tangent complex for the map to the cotangent complex for the source shifted by n-1 is a quasi-isomorphism. And just a remark that I always make in this case, that there is a little bit of a chicken and egg thing. There is no difference between Lagrangian or symplectic structures in this derived world. You can just talk about non-degenerate isotropic structures without mentioning symplectic structures. In particular, an n-1 shifted Lagrangian structure on a map from F to a point is just an n-1 shifted symplectic structure. On the point, there is only one symplectic structure, which is 0. So symplectic and Lagrangian structures are the same type of thing, just one of them is relative to a map, the other is absolute, or relative to the map, to the point. Okay, and so on this moduli of local systems, you get Poisson structures and symplectic structures for the boundary. So if you have a compact-oriented topological manifold of dimension D and a reductive group, then this is an old result. So the boundary of a compact-oriented topological manifold dimension D is a D-1 dimensional oriented manifold. So if you have, say, a d-dimensional oriented manifold, then the derived stack of local systems is 2 minus d-shifted symplectic, which is canonical of the choice of a killing form on your reductive group. And the restriction map, if the manifold is with boundary, the restriction map from local systems on X to local systems on the boundary carries a canonical 2 minus d-shifted Lagrangian structure for the 3 minus d-shifted symplectic structure on the target. And when X is a Riemann surface with boundary, this reconstructs the symplectic structure on the moduli of geolocal systems with prescribed conjugacy classes of monodromes at infinity. So these are local systems, total of local systems with regular singularities in the Ram setting. So if you have a surface with boundary oriented, then the boundary is a disjoint union of finitely many circles. The stack of local systems on the circle is just the adjoint quotient of the group by itself. And you have a product of finitely many copies of those, one for each boundary circle. And it carries a canonical one-shifted symplectic structure by this theorem that I mentioned. And if you choose an element in the group, the inclusion of the conjugacy class of that element in the group gives a canonical Lagrangian structure on the map from the conjugacy class modulo G to the group modulo G. And assigning elements to each boundary component, we get two zero-shifted Lagrangian guys in this one-shifted symplectic space. One is the map from the local systems of the interior of the surface, and the other is the map from the conjugacy classes modulo G. And again, in this old paper, we proved that the fiber product of two Lagrangians in a shifted symplectic guy is shifted symplectic with a shift by one less. So if you have two zero-shifted Lagrangians in a one-shifted symplectic guy, their intersection is a zero-shifted derived stack. And that's really the stack of geolocal systems with fixed conjugacy classes of the local monodromes at infinity. So that's the surface statement with no smoothness assumption. This derived stack of local systems on the surface is actually locally finite presentation. So in the derived sense, it's smooth. And you get the statement everywhere by this Lagrangian intersection picture. And you can also talk about shifted Poisson structures. So if you have a derived algebraic stack, you can look at the de Gillet algebra of n-shifted polyvector fields by looking at shifted cotangent complex, the symmetric algebra of the shifted cotangent complex, global sections on that, and then one global shift. And an n-shifted Poisson structure is just a Mauer-Cartan element in this guy. So it's a map from the graded de Gillet algebra that has k in degree 1, logical degree 1, and graded degree 2 with the zero Lie bracket. So any such Mauer-Cartan element is a Poisson structure. And then a theorem of Melani and Safronov and Castello-Rosenblum and Knighton. So it's a combination of results of these three groups of people. Classifies shifted Poisson structures in terms of symplectic groupoids. So this is a full derived incarnation of the symplectic groupoid program of Weinstein in differential geometry. So it says that shifted Poisson structures always can be described in terms of symplectic groupoids. So the most compact statement in that direction is due to Costello and Rosenblum. if F is a derived algebraic stack, then the space of n-shifted Poisson structures on F is weakly equivalent to the space of equivalence classes of n-shifted Lagrangian maps from F to some formal derived stack F prime, which is symplectic. And so there is some equivalence notion for such maps. If you have one symplectic formal derived stack F prime and another F double prime and two Lagrangian maps from F to F prime and F to F double prime, these two are considered equivalent if there is an n-shifted map, Lagrangian map to a third guy, so that we have a commutative diagram in which the maps from G to F prime and to G to F double prime are étale and compatible with the Lagrangian structures. So up to these equivalences, there is an actual dictionary between Poisson structures and Lagrangian maps to symplectic guys, which is what Einstein actually envisioned in his program. It's just that in differential geometry, this doesn't work quite as well because quotients by foliations are not very well behaved, whereas in this derived work, they're very well behaved. Okay, so an example of that is this Poisson structure on the local system for oriented manifold. If you have a compact oriented manifold X with a boundary dx, then the restriction map is Lagrangian and can be viewed as a 2 minus d shifted Poisson structure on the derived stack of local systems in that infinitesimal sense that I was describing before. Okay, what about symplectic leaves? If you have a Poisson structure on a manifold or on a smooth variety in the usual differential algebraic geometry, it foliates your manifold or your variety by symplectic leaves. For an n-shifted Poisson structure, you don't really have a foliation, you have many different foliations, each of which gives you symplectic leaves. So you can select symplectic leaves for a Poisson structure on a derived stack. So if your Poisson structure is given by a Lagrangian map to something symplectic, then the symplectic leaves are essentially fibers of this map. So you can test that symplectic guy by something other, which is a Lagrangian, and the Lagrangian intersection will be a symplectic leaf for the Poisson structure on F. So a generalized symplectic leaf of F is a derived stack of the form F intersection with lambda, where in F prime, where lambda is another Lagrangian in F prime. And by this Lagrangian intersection theorem, such an intersection carries a symplectic structure, which is n-shifted symplectic. So that justifies the way of thinking of this as a symplectic leaf. Okay. So again, if you have a compact oriented surface with boundary and the restriction to the boundary map that gives you the Poisson structure, then fixing the conjugacy classes gives you another Lagrangian in the boundary, and the Lagrangian intersection between this Lagrangian and this Lagrangian, as I said, is a symplectic leaf. It's the moduli of local systems with fixed conjugacy classes of the monotron matrix. Okay, now let me explain what happens in higher dimensions. So if you have a topological space Y, you can define its boundary. It's a homotopy type in general. It's just the limit of all the compacts, the complements of compacts inside Y. It's not quite a homotopy type, it's a pro-homotopy type. It's a limit inside the homotopy category of spaces. But sometimes, when you're lucky, you can realize this guy as a homotopy type, in fact, not just as a homotopy type, but as a homotopy type of a manifold. In general, it's a non-constant pro-homotopy type. It can be very complicated, but if X is the topological space underlying a smooth n-dimensional complex algebraic variety, then this pro object is equivalent to a constant pro object which has the homotopy type of a compact oriented 2n-1 dimensional manifold. And, oh, okay, there is a typo here. This is supposed to say boundary. This dx guy is the homotopy type of the boundary of the simple or real-oriented blow-up of a good compactification of Z along a normal crossing boundary. And it doesn't depend on the compactification as a topological manifold. As a manifold with corners, it does depend on compactification. So if you're doing a stratified version of this statement, then it becomes more interesting. But if you're looking at that it as a topological manifold, it doesn't depend on compactification. And okay, so you get this statement that the canonical map induces a restriction of derived Artin stacks locally finite presentation, and this is a Lagrangian map, and that Lagrangian map has a shifted Poisson structure, which is the one that you have for CW complexes, for manifolds, that Max mentioned at the beginning. Okay, the symplectic leaf story is more delicate. So assume that we fix a compactification, a smooth compactification, and this script Z compactification, I'm assuming, is obtained by adding a boundary which is, say it's a union of smooth divisors. And I'm going to say something about the normal crossing case in a moment. But suppose that there is a compactification in which the boundary is smooth. Then the manifold I'm talking about is just the total space of an oriented circle bundle over that smooth divisor. That circle bundle for each component is classified by the first-gen class of the circle bundle, so it's given by a class in H2 of the component with coefficients in Z. And if you fix an element in the group with centralizer Zi, the circle acts on the classifying space, the classifying stack of that centralizer via lambda I, and it acts naturally on G mod G, so that the Lagrangian structure on the map from the classifying stack of Zi to G mod G is S1 equivariant. And then you can use these equivariants to twist by the first-gen class of the circle bundle. So you get a locally constant family of classifying spaces for Zi over the divisor, corresponding to that alpha I guy, goes to a locally constant family of stacks G mod G over the divisor. So it's not constant, but it's locally constant, and they're both classified by alpha I. And then you just need to look at sections of these locally constant guys. You look at maps from the boundary to these locally constant families, sections, and a lot maps to the locally constant family of centralizers. So in particular, you know, this family of stacks should have sections in order to have non-empty stacks. These discrete invariants should exist in order to have non-empty moduli. So these are local systems on the I twisted by alpha, and you get this canonical orientation on the divisor, which induces a 3 minus 2n shifted symplectic Lagrangian morphism between these guys. And so you get a Poisson structure, and you can intersect with another Lagrangian guy coming from the lambda i's, and you get a 2 minus 2n shifted symplectic structure on that Lagrangian intersection. So up to this twist by the normal bundles to the divisors, if the divisor is smooth, you get exactly the statement that you would expect from the topological case when you're dealing with a manifold with boundary. When the divisor is with normal crossings, when it has components that intersect, actually there is a non-trivial condition. Okay, so yeah, I just stated the statement about the generalized symplectic leaf in the smooth divisor case. But when the divisor is with normal crossing, you get a non-trivial condition. So the boundary in the compactification, in the algebraic compactification, say it has two components intersecting transversely, and each of them is smooth, and the intersection is say smooth. It doesn't have to be connected, but say it's connected. Then the boundary, it's gluing of two circle bundles. One, a circle bundle of D1 minus the intersection, the other a circle bundle of D2 over D2 minus the intersection, the normal bundles. And you're gluing over the torus bundle, which is the normal bundle to the intersection. It's the S1 cross S1 bundle, which is the normal bundle to the intersection. And each of these guys has a homotopy type of an oriented manifold with boundary, and you glue along that boundary, and you get a manifold, 2n minus 1 dimensional manifold. And you have to have a commuting pair of elements, right? Because the local monodrome is near the intersection they commute. So if you start with a commuting pair of elements, you get a map from the intersection of those two guys over the local systems of the intersection to the local systems on the boundary and the local systems on the boundary with fixed monodrome on the intersection. And it comes equipped with a natural Lagrangian structure. So that's the Poisson statement that gives you the Poisson structure. But if this pair of commuting elements is special, if it satisfies the strictness property, then this this stack is also comes equipped with a Lagrangian with a symplectic structure, and it is a symplectic leaf in the local systems.
So can you write what is strict?
Yeah, so I'm going to say what strict is. I just need to click on this. On this yellow thing here. Thank you. Okay, so here is the strictness statement. A pair of commuting elements in a reductive group is called strict. So I'm going to say it in terms of stacks, and then I'm going to say it purely algebraically. So it's called strict if the map from the classifying stack of the stabilizer of the two elements to the quotient of Z1 by Z1 with intersection of Z1 by quotient by Z1, Z2 quotient by Z2 in the moduli stack of commuting pairs of elements in G is Lagrangian. So it's a symplectic condition. But it's actually a group theoretic property, which, as I said, was discovered by Victor Ginsburg. What it says is, it says that if you have a pair of commuting elements in the reductive group G, and if you look at the identity minus the adjoint action of one of the elements, and the identity minus the adjoint action of the other element, as endomorphisms of the Lie algebra, then what you need to know is that the element U is strict with respect to the kernel of V. So, in fact, if you think about this as an important element and you look at the monodromy weight filtration for that important element, it means that U is strict with respect to that filtration. But the linear algebraic property is this, it's just that the image of V restricted to the kernel of U is the intersection of the image of V intersected with the kernel of U. And it's a symmetric property by the symplectic definition. From this definition, it's not completely clear that it's symmetric. It's actually a theorem of Ginsburg that it's symmetric. But in fact, you can prove that this is exactly the same symplectic condition that I stated. And so what we prove is that this is a sufficient condition for the local monodromy so that you get actually a symplectic leaf. We conjecture that it's necessary, but we haven't proven it. But we do have examples of non-strict pairs where the fixing the local monodromy to be non-strict does not give you a symplectic leaf. So it's certainly weaker. It's certainly a stronger condition than being a symplectic leaf. I do believe it's equivalent, but we haven't proved it. How am I doing with time?
So you have 5 more minutes.
5 more minutes. Okay.
No, you end up 17:50, so you still have 17 minutes.
Okay, great. Okay, so these are just some easy ways to enforce strictness. So if one of the elements is semi-simple, then the pair is always strict. If you have a principal nilpotent pair, then it's strict. For example, if you have a non-principal unipotent pair, if you have a unipotent element and the same unipotent element as the commuting pair, then in general this is not strict. And this actually gives you a non-Lagrangian leaf. Can you click on the button? Thank you. Okay. And so now I'm switching gears and I'm going to talk about the Deran story. So this strictness condition is really a necessary, a sufficient condition that one needs to impose. And it's the same in the, if you want to do the Stokes local systems. There is a whole version of this Betty story which works in the irregular case when you do the Stokes filtered local systems, and you need to impose it on the form of monodromy, in higher dimensions. Okay, so now suppose I have a smooth variety and take the Deran functor of x. So this is the functor that sends each commutative differential graded algebra to the points of x over the spectrum of the reduction of that algebra. So it kills all the higher homological elements and it kills all the nilpotents, and you get just the points over that algebra. And the derived stack of perfect complexes on the variety is by definition just the maps from that Deran stack to the stack of perfect complexes. And if x is not proper, this guy is non-representable. It's not a finite type even as a int stack. It's a mess. If you want to study it, you can finagle things. So if you take x and write it as a finite colimit of affine schemes, and you view this stack of perfect complexes as a mapping stacks, then you can check that this stack of perfect complexes, even though it's not representable, it has good infinitesimal properties. If x is a smooth algebraic variety, then this is it satisfies these Artin-Lurie representability conditions, part of the Artin-Lurie representability conditions. It's nil complete. It behaves well with respect to infinitesimal thickenings, and it's infinitesimally Cartesian. It satisfies the first Schlesinger conditions. And it has also a cotangent complex, which is perfect at all field valued points. It's not perfect in general, but at field valued points it's perfect. And if you want to force it to be perfect in general, you need some flat home conditions at infinity, which are fairly hard to enforce, even though there is some recent work of Sabah that helps with that, but I haven't quite explored it. Okay, now fix a good compactification with simple normal crossing divisors at infinity. If you take the ideal, probe your compactification by an affine étal map, an étal map from an affine guy, pull back the ideal of the divisor, complete with respect to that ideal, and then you can define the derived stack of perfect complexes on the completion, or the derived stack of perfect complexes on the punctured formal neighborhood to infinity. by using these test guys. So you can look at for a test-derived scheme, you can look at the completed tensor product and the spectrum and perfect complexes on that guy, or the spectrum. So this formal spectrum minus the variety given by the ATO. And so this is actually a famous theorem in some other version is the theorem of Hennian, Porter, and Vesozzi, but in the analytic context is the whole theorem of Ben-Basat and Tionkin. And it says that the global points, the category of global points of this guy is independent of the choice of good quantification. So you can think about this as the Schiff category of perfect complexes on the punctured formal neighborhood infinity. Right. So for a variety, this is for smooth varieties. This is proven. You would expect that it's true for testing not with the spectrum of a field, but with any say affine derived scheme. But it's a known. It's a known, and somehow this method of Ben-Basat and Tionkin or of Efimov, it doesn't work for digi schemes or for singular affine schemes. It just doesn't work. I mean, I believe it's true, but we don't know if it's true. But at least for points, or for close points, it's true. And then to circumvent that, actually, Efimov invented these extendable perfect complexes. So you can look at the Karoubian image of the complexes that extend to the formal completion of the compactification along the divisor. So extend from the punctured formal neighborhood to the formal completion. And then for any test digi scheme, locally defined presentation, this is independent of the compactification. The category is independent, and in fact, if you solve the moduli problem over derived schemes for that category, it's also independent of the compactification, which is something we checked with Bertrand. So this first part is Efimov's theorem. And now you can use this to construct the categories and the moduli of perfect complexes with flat connections on the formal boundary, on the punctured formal neighborhood at infinity. You just mimic it by doing completions of the RAM algebras for test guys. And then you can prove that you get a well-defined digi category of graded mixed modules, which are locally free of weight 0, and that the pre-stack that you get this way is exactly what you get by forgetting the connections and looking at the extendable perfect complexes after forgetting the connection. And the theorem is that these are stacks. They're not just pre-stacks. You don't need to stackify. They're independent of the compactification. The restriction map is a map of derived stacks which factors through the extendable guys, and the stack of perfect complexes with flat connections on the punctured formal neighborhood to infinity has all the good infinitesimal properties. It's nil complete, infinitesimally Cartesian, has a cotangent complex. The cotangent complex is perfect over the field points. And then the theorem, as I stated it, says that that map carries a natural 2 minus 2n shifted isotropic structure. It is Lagrangian over field value points, because for Lagrangian you need to know perfection, and so we need to restrict to the field value points. Actually, after that, I have just explanations of things that I skipped explaining, so I think I'll stop here.
Any questions for Tony?
Yes.
So below there, I see Betty, the RAM. It looks like, what about Hodge?
Yeah, so there should be a Dolbo version of this. Yeah, but it's much more difficult to define, and we tried, but these extendability conditions are very hard to control in the Dolbo version. You know, this is very similar to saying, you know, looking like a Simpson statement that the digi category, say even on a compact Keller manifold, right? The digi category of complexes of flat connections, complexes of vector bundles with flat connections, is equivalent to the digi category of semi-stable Higgs bundles, right? It's not equivalent to the digi category of Higgs bundles, it's equivalent to the digi category of semi-stable Higgs bundles. And it's a completion statement, right? You prove it for the semi-simple objects, and then you look at the completions and prove a uniqueness of completion. So you need to find some analog of semi-stability for these objects on the formal boundary, so that you can anchor your Higgs bundles in order to be able to prove this type of statement. And we looked at, you know, so there is this famous Mochizuki condition of the Higgs bundles at infinity being locally abelian, which is what allows you to talk about semi-stability. And so you definitely need that. And we looked a little bit at the strictness condition to see how it interacts with the locally abelian condition. It interacts very well. But we still don't know what the correct stability condition is. So anyway, it should exist, but I don't know what the correct statement is. And I mean, to be continued.
Sorry, I always have a question. Not actually a question, but a comment. A very long time ago, around 2000, Kajdan asked me the following question. It was, if you can more or less think intersection homology of singular variety as common part of homology of all possible blobs. And this question also is kind of dual question. Suppose you have smooth but non-compact variety, consider all possible complications. Is it some kind of natural common part of these complications? And I invented some answer, and it was a very similar story, because it's essentially in homology of the boundary. You should find. Can you give? Essentially, in homology of the boundary, to a tubular neighborhood of infinity, you should find some Lagrangian subspace, and it will be like tangent complex with trivial connection. And this natural tangent Lagrangian subspace, but on level of homology, consider in ice homology of boundary, consider ice term of weight filtration. Right. Yeah, but yeah, this was a great answer, but it didn't work because it's not canonical object derived category. But it's kind of like Hodge direction to make different Lagrangian things instead of topological one coming from Hodge theory.
Yeah, I mean, there is something like that you need to do for the symplectic leaves. You need to fix this Lagrangian.
Yes, it will be kind of not per capital this bit
and
just only the ramp.
Just in the But yeah, I mean, already the category is kind of clear. So for the Dolbo case. Vivek.
Can you go back to this disability, the special condition?
The strictness?
Strictness.
Okay. Yeah, it's here.
Okay, here,
This one, or the symplectic one. Huh?
What was the statement that you need strictness for?
Oh, you need strictness to see. So you have local systems on your open variety. That's Poisson. You want to ask what condition. So you want to say, oh, I want to fix conjugacy classes of local monodromies around the components at infinity, and get something symplectic. Right? That's how the symplectic leaves normally work. So if you have two components that intersect, you fix conjugacy class, you fix two commuting elements, and you want to say that these local systems with fixed conjugacy classes by those two commuting elements is symplectic. It's not in general true if the elements are arbitrary commuting elements. They have to be a strict pair of commuting elements.
This has nothing to do with the interior. This is just to talk about.
Yeah. This is a statement about the local monodromies at infinity giving you something Lagrangian.
Oh, okay.
Yeah, it's just this statement. It's just because they have an intersection.
In the smooth case, you just have conjugacy class.
Yeah, in the smooth case, it's just one guy, and then there is no condition. Yeah. In the smooth case, it's exactly as occurs. I mean, there is a slight twist by the normal number, but yeah, it has nothing to do with interior. It's just a local statement at the boundary. Back to Chen.
Thank you. Thank you for this nice time. See you tomorrow then.
Yeah,